Hello there, and welcome to Life Beyond Seen, where curiosity slows down, science speaks softly, and the world becomes just a little larger before sleep. Tonight, we are drifting toward a place that most of us will never see, not because it is hidden behind a locked door or lost behind a mountain, but because it lies beneath miles of dark water, beyond the reach of sunlight, beyond easy maps, and far beyond the comfort of an ordinary human breath. Our quiet journey tonight takes us north of Puerto Rico, out over a stretch of blue ocean that, from above, looks calm enough to cross without much concern. A ship may pass over it, clouds may cast shadows on it, flying fish may break the surface for a moment and vanish again. To the eye, it is just sea, wide and bright and moving in the usual way. But far below that surface, the floor of the Atlantic drops into one of the deepest places on Earth. The Puerto Rico Trench sits there like a long, steep wound in the ocean floor, a place where the planet is not smooth or simple, but folded, pressed, fractured, and still restless. It is easy to forget that the ocean has shape. We often picture it as a flat sheet of water with waves on top, as if the seafloor beneath it were some gentle sandy bottom waiting politely below. But the ocean has cliffs, plains, ridges, slopes, canyons, valleys, and trenches. Some of those trenches are so deep that if you could place the tallest mountain on land inside them, there would still be seawater above its peak. That is not a comfortable thought, especially if you're listening in bed with a nice pillow and perhaps a cup of tea nearby. It is one thing to imagine the ocean as a holiday postcard. It is another to remember that parts of it are deep enough to swallow entire landscapes. The Puerto Rico Trench is the deepest part of the Atlantic Ocean. It lies close enough to familiar islands that it can seem almost surprising. This is not some distant feature hidden at the far edge of an empty world map. It is near Puerto Rico, near the US Virgin Islands, near places where people live, work, sleep, drive to the shops, complain about traffic, and decide whether they really need one more coffee. And just north of all that ordinary life, the seabed falls away into a darkness that remains difficult to visit, difficult to measure, and difficult to understand. So tonight, the question is not simply, why have we not explored it? Humans have explored pieces of it. Ships have crossed it. Scientists have mapped parts of it. Instruments have been lowered into it. Submersibles have entered some of its depths. The question is more careful than that. Why can we not truly explore the Puerto Rico Trench in the way we explore a forest, a desert, a cave, or even the surface of Mars? Why is a place on our own planet still so hard to know? That is the strange thing about the deep ocean. It belongs to Earth completely, and yet it often feels less reachable than space. We can look up at the moon with our own eyes, but we cannot look down into the Puerto Rico Trench without machines, cables, sonar, pressure housings, ships, funding, patience, and a great deal of luck. The trench is not far away in a cosmic sense. It is not beyond the solar system. It is not even beyond our atmosphere. It is right here, on the same planet as bakeries, streetlights, laundry baskets, and that one kitchen drawer full of things no one can identify. And still, it resists us. Before we go deeper, I would love to know where in the world you're listening from tonight. Are you near the sea or far inland? Can you hear traffic outside, rain at the window, a fan turning in the room, or maybe just the quiet little sounds a house makes when everyone has finally stopped asking it to do things? And if you have ever stood beside the ocean at night, looking out into the dark water, did it feel peaceful to you? Or did some small part of your mind remember that the surface is only the beginning? It is a fair thing to wonder. The sea can be beautiful in the friendliest way. It gives us beaches, salt air, fishing boats, bright shallows, coral reefs, and that oddly determined habit of filling shoes with sand no matter how careful we are. But the same sea also contains places where the pressure is strong enough to crush ordinary machines, where the temperature drops, where sunlight has never arrived, where sound behaves strangely, and where the seafloor itself may shift because tectonic plates are still slowly pushing, sliding and grinding past one another. The Puerto Rico Trench is not just deep. Depth alone would be enough to make exploration difficult, but this trench adds more complications. It is part of an active and complicated boundary between great pieces of Earth's outer shell. The North American plate and the Caribbean plate meet in this region, and they do not meet like two polite neighbours leaning over a garden fence. They press, scrape, bend, and interact in ways that can produce earthquakes and shape the seafloor. The trench is not a quiet bowl sitting at the bottom of the ocean. It is part of a living geological system, though living here does not mean breathing or blinking. It means moving slowly, storing stress, releasing energy, and changing across time in ways that are hard for us to watch directly. And direct watching is where the problem begins. On land, if scientists want to study a mountain, they can climb it, walk around it, take samples, set up instruments, return next week, and complain about the weather with some authority. If they want to study a volcano, they can place sensors on its slopes, photograph it, measure gases, and keep returning until their boots have suffered enough. If they want to study a forest, they can walk beneath the trees and count what lives there. Even in Antarctica, which is hardly a comfortable field trip, researchers can stand on the ice, drill, sample, and build stations with walls, heaters, and mugs that say something cheerful about science. The Puerto Rico Trench offers no such courtesy. You cannot stand in it. You cannot stroll across it with a notebook. You cannot hammer a little sign into the mud saying, "Research area, please do not disturb." To reach it, you must first cross the ocean above it, then send instruments down through thousands upon thousands of meters of water. And the deeper those instruments go, the more the ocean presses on them from every side. At the surface, pressure is familiar. We do not notice it much because our bodies are built for it. A few meters underwater, your ears begin to remind you that pressure is real. Go deeper, and the reminder becomes less polite. At the bottom of a trench, pressure is not a reminder. It is a constant force. That pressure changes everything. It changes what vehicles can be built from. It changes how electronics must be sealed. It changes how cameras are protected. It changes how lights are mounted. It changes how samples are collected. It changes how long a mission can last, how much it costs, and how much can go wrong. A small leak at ordinary depth is inconvenient. A small leak in the deep ocean can destroy equipment very quickly. Water does not need to be dramatic about it. It simply enters where it is not supposed to enter, and the mission is over. This is one reason the deep ocean often feels like a place that refuses to become familiar. Every visit is expensive. Every descent takes planning. Every hour at the bottom has to be earned by ships, crews, engineers, weather windows, permissions, cables, batteries and instruments that have all agreed, for the moment, not to fail. And if something breaks, no one can step outside and fix it with a wrench while muttering under their breath, which is how many of humanity's greatest repairs begin. At trench depths, there is no casual repair. There is only recovery, redesign, and a quiet hope that the next attempt behaves better. Still, we are very good at trying. Humans are persistent creatures. We have looked at mountains and decided to climb them. We have looked at deserts and decided to cross them. We have looked at the sky and decided to leave the ground, which remains one of our more surprising decisions. So naturally we look at the Puerto Rico Trench and want to know what is down there. We want maps. We want images. We want samples. We want to understand the geology, the hazards, the life, the sediments, the strange chemistry, the hidden slopes, and the history written in layers of mud and rock. But wanting to know a place is not the same as being able to know it fully. That is the gentle frustration at the centre of tonight's story. The Puerto Rico Trench is not unexplored because no one cares. It remains hard to explore because the trench is deep, active, remote in the practical sense, expensive to reach, dangerous for equipment, and complicated in ways that do not fit neatly into a single expedition. And then there is the matter of darkness. Sunlight does not reach the deep trench. The bright surface world ends far above it. Down there are no sunlit waves, no blue shallows, no drifting beams of afternoon light. Any camera that wants to see must bring its own light. But light in the deep ocean is not like sunlight spread across a field. It is a small cone, a limited patch, a narrow view. A remotely operated vehicle may illuminate a few meters ahead, perhaps a slope, a rock, a pale animal, a cloud of sediment disturbed by its own movement. Beyond that, the darkness returns. It is not an enemy. It is simply the normal condition of the place. Imagine trying to understand an entire city at night by walking through it with a torch that only lights a few steps at a time. You could learn a lot. You could notice walls, doors, signs, drains, insect, cracks in pavement, and maybe one very confused pigeon. But you would not quickly understand the full city. You would need maps from above, measurements from the ground, repeated visits, and a way to connect tiny observations into a larger picture. That is the trench. Sonar can give us broad shapes. Cameras can give us close details. Samples can give us physical evidence. But turning all of that into true understanding takes time, and the trench does not make that time easy. If you find this kind of slow journey soothing, or if you enjoy drifting through science without being shouted at by urgent music and alarming graphics, I would be ever so grateful if you liked the video and subscribed. It helps this quiet little corner of the internet reach other curious minds who might also enjoy learning about deep places while becoming slightly less determined to stay awake. And if you already know someone who loves the ocean, fears the ocean, studies the ocean, or insists they would absolutely survive in a submarine despite getting nervous in elevators, perhaps share this with them too. Tonight's subject has a way of humbling us. The Puerto Rico Trench reminds us that Earth is not fully open to us just because we live on it. We often speak as if the modern world has mapped everything. We carry phones that can show us streets in cities we have never visited. We can zoom in on rooftops, roads, rivers, farms, stadiums, airports, and the unfortunate layout of our own back gardens. It can feel as if the planet has become completely visible. But most of Earth is covered by ocean, and much of that ocean floor has not been explored in fine detail. The surface world gives us a false sense of completion. We see the blue on a map and think the blue has been understood. It has not. The blue is a cover. Beneath it are places where the maps are still improving, where measurements are still being corrected, where living things are still being discovered, where faults and slopes are still being studied, and where the difference between what we know and what we imagine remains large enough to be uncomfortable. The Puerto Rico Trench is one of those places. It is a known place, yes, but known does not mean familiar. It has a name, it has a location, it has measured depths, it appears on maps, yet a named mystery is still a mystery. Giving something a label is useful, but it's not the same as sitting beside it with a lamp and taking a long, careful look. There is also a very human reason the trench matters. It is not only a scientific curiosity, it sits near communities. The tectonic forces around it are part of a larger system that can produce earthquakes and tsunamis. Understanding the trench is not merely about satisfying curiosity, though curiosity is a fine and underrated thing. It is also about understanding risk. It is about knowing how the seafloor is shaped, how faults behave, where landslides might happen, how sediments move, and how energy can travel through water toward coastlines where people are not thinking about geology at all. They are thinking about dinner, school, family, bills, weather, and whether they remember to buy milk. That is often how natural hazards work. They begin in places most people cannot see. A fault slips offshore. A slope fails underwater, a wave forms far from the beach. Then the effects arrive in the human world, where everything suddenly becomes urgent. The deep ocean seems remote until it is not. The Puerto Rico Trench may lie beneath miles of water, but it is connected to islands, shores, harbours, homes, and histories. That connection makes the trench more than a dark line on the seafloor. It makes it part of the lived world above it. Yet even when the stakes are clear, exploration remains difficult. Research ships are limited. Deep-sea vehicles are limited. Funding is limited. Weather is not always cooperative. The ocean is not a laboratory with a roof and a convenient kettle. It moves, it storms, it corrodes, it hides. Saltwater is remarkably good at finding ways to make expensive equipment regret its life choices. Cables strain, batteries drain, currents shift, sediment clouds rise when disturbed and make cameras temporarily useless. Acoustic signals can be affected by distance and conditions. A plan that looks sensible on land may become awkward once the ship is rolling. The wind has changed and a machine the size of a small car is dangling over the side on a cable longer than most people care to imagine. There is something almost funny about how much effort it takes to look at our own planet. We can build satellites to watch hurricanes from space, but to inspect the bottom of a nearby ocean trench, we still have to lower machines into darkness and hope the sea allows the visit. It is a little like owning a very large house and realizing that the basement is deeper than Mount Everest is tall, filled with pressure, darkness, strange animals, unstable geology, and no stairs. Naturally, someone then says, well, we should go have a look, because that is what scientists do. Sensible people might pour another cup of tea and think about it. Scientists begin designing the pressure housing. The pressure, the darkness, the geological activity, the cost, the limited access, the patchy maps, the difficulty of sampling, the danger to equipment, and the sheer size of the place all combine into one simple problem. The Puerto Rico Trench is not impossible to visit, but it is very hard to truly explore. A visit gives a glimpse, a dive gives a path, a sonar pass gives a shape, a sample gives a clue. True exploration requires many glimpses, many paths, many shapes, many clues, and enough patient work to connect them. The trench is not a single object waiting to be photographed. It is a huge, uneven, changing environment, and understanding it means returning again and again. That is where tonight's journey begins, not with the idea that the trench is completely unknown, and not with the idea that humans have failed, but with something more honest. We know enough to understand that it matters. We do not yet know enough to say we truly understand it. The deep ocean keeps teaching us this lesson. It gives us a measurement, then asks for better measurements. It gives us a map, then reveals the map is too coarse. It gives us a strange creature, then hints that there may be many more nearby. It gives us a fault, a slope, a sediment layer, a signal, a question, and then quietly waits beneath all that water while we work out how to come back. So settle in, slow your thoughts, and let the surface world become still for a while. Imagine the warm lights of Puerto Rico behind us, the dark Atlantic ahead, and beneath the ship far below the moving waves, the seafloor beginning to tilt downward into one of the least forgiving places on Earth. We're not rushing there. We're not dropping suddenly into the dark. We're starting at the edge, where the ordinary ocean begins to hide an extraordinary depth, and where a place that seems close on a map becomes, in practice, one of the hardest rooms on Earth to enter. If we stay for a while above the ocean north of Puerto Rico, nothing at first appears unusual. The water does not come with a warning label. There is no neat line painted across the waves saying, "This is where the Atlantic begins to drop." A boat moving across the surface might rise and fall gently with the swell. The sky might be bright. The air might smell of salt and warm weather. Somewhere behind us, the island carries on with ordinary life, with roads, lights, music, kitchens, late dinners, early alarms, and people going about their day with no need to think about the enormous shape of the seafloor nearby. That is one of the strange things about the Puerto Rico Trench. It is close to places that feel familiar, but it belongs to a world that does not. From the shore, the sea can look simple: blue water, bright horizon, maybe a few clouds sitting above it like they have nowhere better to be. But under that surface, the land does not continue gently forever. The underwater edge north of Puerto Rico changes into a steep and complicated system of slopes, valleys, ridges, and deep basins. Farther out, the seafloor falls into the deepest place in the Atlantic Ocean. This is not the kind of depth that is easy to picture. Numbers help a little, but only a little. We can say the trench reaches more than 8 kilometers down, or nearly 5.5 miles, but the mind has a habit of turning large numbers into decoration. It hears them, nods politely, and then places them in the same mental drawer as the distance to the moon, the number of stars in the galaxy, and how many unread emails a person can reasonably ignore before calling it a lifestyle. So it helps to slow the number down. 8 kilometers is the height of many commercial flights when they are already far above the clouds. It is far taller than most mountains people will ever see in person. It is deep enough that sunlight has no business being there. It is deep enough that the water above presses down with a force that makes the surface world seem almost delicate. If you could take a city street, turn it upright, and lower it into the sea, the trench would still keep going after the buildings, the church towers, the apartment blocks, and nearly everything else had disappeared behind you. And yet, at the surface, there is only water. This makes the trench difficult to respect in the way we respect visible dangers. A volcano has a shape. A cliff has an edge. A storm announces itself with wind, rain, and the very clear feeling that perhaps the washing should not have been left outside. The Puerto Rico Trench is quieter than that. It hides beneath one of the most ordinary-looking surfaces on Earth. The ocean gives no easy clue that below it lies a place where the planet has folded itself into a deep line of pressure and shadow. If you were floating above it, you might feel the boat move. You might hear the engine. You might see a bird pass overhead. Nothing in that moment would let your body understand what is beneath you. Your instincts were built for land, for trees, slopes, caves, fire, animals, weather, and other people. Your instincts are not very good at understanding a trench under several miles of seawater. They do not send up a warning saying, "Excuse me, but the floor of the Atlantic is missing beneath us." So the trench remains mostly an idea until science gives it shape. That shape is not neat. The Puerto Rico Trench is often described as a long depression in the seafloor, but even that can make it sound simpler than it is. A trench is not like a clean cut made with a knife. It is a region of twisted geology where the outer shell of the Earth has been pushed, pulled, bent, cracked, and dragged into forms that can only be understood through measurement. The seafloor around Puerto Rico includes steep slopes, fault systems, submarine canyons, ridges, and sections where sediment gathers in thick layers. Some of those layers are quiet records of the past. Some may be disturbed by earthquakes or underwater landslides. The trench is not just a hole, it is a record of movement. The reason it exists has to do with tectonic plates, those huge pieces of Earth's outer layer that move slowly across the planet. They move so slowly that if you sat and watched them, you would mainly achieve sore legs and possibly a very strong opinion about boredom. But over millions of years, slow movement becomes mountains, islands, earthquakes, trenches, and entire ocean basins. In the region around Puerto Rico, the North American plate and the Caribbean plate meet in a complicated way. They do not simply collide straight on in a tidy classroom diagram. Their interaction includes sideways motion, compression, bending, and faulting, and it is messy because Earth is under no obligation to be convenient for textbooks. This plate boundary is one reason the seafloor there is so difficult to understand. A simple trench might be hard enough. A deep trench beside an active and complicated plate boundary is another matter. The ground is not sitting there like a museum exhibit. It is part of an active system. Earthquakes can occur in the region, stress can build and release, slopes can fail, sediments can shift. The shape of the seafloor is connected to forces much larger than anything a ship or robot can control. That makes the trench both fascinating and important. It is fascinating because it shows us how Earth builds and breaks its own crust. It is important because those processes do not stay politely at the bottom of the sea. They can affect people living on nearby islands. Earthquakes and tsunamis are part of the hazard story in the northeastern Caribbean. To understand those hazards better, scientists need to understand the underwater landscape, the faults, the slopes, and the sediments. They need to know where the seafloor is stable, where it has moved before, where it may move again, and how energy might travel through water if the system changes suddenly. But the ocean makes this work slow. On land, a mountain casts a shadow in sunlight. You can see where it rises. You can walk around it. You can argue with your hiking partner about whether the path is really almost there, which it almost never is. In the ocean, the trench casts a different kind of shadow. It is not a visible darkness on the surface. It is a gap in direct experience. It is a place we know through instruments, through sonar beams, through gravity measurements, through seismic data, through samples brought up from below, and through rare images from deep vehicles. We know it by evidence, not by presence. This is why maps of the seafloor matter so much. A map turns hidden shape into something the mind can hold. Without mapping, the trench is only a name and a depth. With mapping, it becomes slopes, scarps, basins, ridges, channels, and features that can be compared and studied. But mapping the deep ocean is not like taking a photograph from above. Satellites can map land in extraordinary detail because light reflects off the surface. The seafloor is hidden beneath water, and water blocks the simple view. To map it properly, ships use sound. Sonar sends sound pulses down into the sea and measures the echoes that return. From those echoes, scientists build a picture of the bottom. It sounds straightforward until you remember the scale. The ship is at the surface. The seafloor may be several miles below. Sound travels through water, but not instantly. It moves down, bounces back, and carries information with it. The deeper the water, the wider and more complicated the measurement becomes. The ship must move in planned lines. The instruments must be calibrated. The speed of sound in seawater changes with temperature, pressure, and salinity. So those conditions must be measured too. The data must be cleaned and processed. A map is not simply collected. It is built carefully, piece by piece, from echoes. Even when sonar has mapped a region, it does not show everything. It gives shape, and shape is valuable, but it does not automatically reveal what the surface is made of, whether it is soft sediment, exposed rock, loose debris, biological growth, old landslide material, or something stranger. For that, scientists need samples and images. A map may show a slope. A camera may show that the slope is covered in fine mud, scattered rocks, corals, sponges, or tracks left by animals. A sample may reveal age, chemistry, grain size, and history. Each tool answers one kind of question and creates several more, which is one of science's favourite habits. The trench beneath Puerto Rico also challenges us because it is large. We often talk about famous deep places as if they are single points, as if the deepest part is the whole story. But the deepest point is only one part of a much bigger system. A trench is not just its maximum depth, any more than a country is just its highest mountain, or a person is just their worst driver's license photo. The important details are spread across a wide area. There are approaches, walls, nearby basins, fault zones, channels, and connected structures. To truly explore it, scientists need to understand the broader setting, not just visit the deepest spot and declare the mystery solved. That is where the phrase truly explore becomes important. It is possible to reach a place and still not understand it. A robot can descend into the deep, switch on lights, record video, and return with extraordinary footage. That is exploration. Yes, but it is only one line through a very large darkness. Imagine trying to understand Puerto Rico itself by driving one road at night with your headlights on, then leaving and saying you have seen the island. You would have seen something real. You might have seen buildings, trees, hills, animals, and perhaps one extremely confident chicken. But you would not know the whole place. The trench is the same, except the road is water, the headlights are mounted on a deep-sea vehicle, and the chicken is probably replaced by a pale fish that looks like it has heard disappointing news. The deep ocean also hides distance in a way land does not. On a map, the trench may appear close to Puerto Rico. In practical terms, distance is not just horizontal, it is vertical too. A site may be only a reasonable ship journey from shore, but the moment researchers need to work at great depth, everything becomes more difficult. The vertical distance becomes part of the expedition. Lowering equipment takes time. Retrieving it takes time. Sending commands through cables or acoustic systems takes planning. Every descent has a beginning, a middle, and a long wait before the seafloor appears. There is also the matter of weather. A trench may be deep and still be controlled, in practical terms, by the surface. Research ships operate in the real ocean, not in a diagram. Waves, storms, currents, and wind can affect whether instruments can be deployed safely. A robot may be built to handle pressure at depth, but the ship must still be able to lower it into the sea. The crew must still work on deck. The cable must still behave. A calm seafloor does not help much if the surface is throwing the ship around like a toy in a bathtub, and if you have ever tried to pour tea on a moving train, you have a very small and domestic hint of what motion can do to precision. The trench's long blue shadow, then, is not only its physical depth, it is the way that depth reaches into every part of exploration. It affects the maps. It affects the machines. It affects the cost. It affects the risk. It affects how long scientists can observe, how much they can sample, and how often they can return. The ocean is not merely something above the trench. It is the main obstacle between human curiosity and the place we want to understand. This can feel strange because the trench is part of our own planet. We're used to thinking of Earth as home, and home is supposed to be accessible. If there is a room in your house you cannot enter because the pressure would crush your furniture and the darkness requires a specialized lighting system, you may begin to question the estate agent. But Earth is like that. It has rooms we can only enter briefly and carefully. The deep ocean is one of them. The Puerto Rico Trench also carries a sense of nearness that makes the mystery more unsettling. It is not hidden in the middle of nowhere, in the way people often imagine deep-sea places. It lies beside a populated region with a long human history. The waters around Puerto Rico and the Virgin Islands have been travelled, fished, studied, and lived near for centuries. People have watched the sea there in calm weather and storms. They have depended on it and feared it. And beneath that same water is a feature that remains difficult to inspect in detail. This closeness creates a useful reminder. Mystery does not always live far away. Sometimes it sits beside the familiar. A person may know the streets of San Juan, the curve of a beach, the sound of rain on a roof, and still live near a deep-sea landscape that no human eye has fully taken in. The surface world and the hidden world occupy the same geography. One has music, traffic, food, conversations, and warm lights. The other has pressure, darkness, sediment, fault lines, and slow geological force. They are neighbours, though one of them is much less likely to answer the door. There is something humbling in that. Modern life gives us the feeling that everything can be checked quickly. We search, zoom, tap, refresh, and expect answers to appear. The Puerto Rico Trench does not respond to that kind of impatience. It asks for ships, time, instruments, expert crews, and repeated missions. It asks researchers to accept partial knowledge and build patiently from it. It reminds us that a place can be known in outline and still remain largely unvisited. It can be mapped in broad strokes and still hide fine details. It can be close enough to matter and deep enough to resist. In the long view, this resistance is not failure. It is simply the nature of the place. The trench was not made for human access. It was made by plate movement, gravity, sediment, water, and time. It does not care whether our cameras have enough battery. It does not care whether a grant proposal was successful. It does not care whether a cable snags, a sensor fails, or the ship has to leave because the weather has turned. That indifference is part of what makes deep ocean science so demanding. The trench is not hostile in a dramatic way. It is not trying to keep secrets. It simply exists under conditions that are very different from ours. That difference begins almost immediately below the surface. The first meters of ocean are still connected to the world we know. There is light, warmth, movement, and familiar life. Go deeper, and the light weakens. Colours fade. Red disappears first, blue remains longer, then fades too. The water cools, the pressure rises. The open sea becomes less like a bright place, and more like a vast column of weight. By the time we think about the trench floor, the surface world is no longer physically present in any ordinary sense. There is no day or night down there as we experience it. No sunrise, no weather, no horizon, only darkness, pressure, cold, geology, and life adapted to conditions that would end our visit almost instantly without technology. Yet the trench is connected to the surface by more than water. Material falls from above. Tiny particles, dead plankton, dust, waste, and bits of biological matter drift downward through the ocean in what scientists sometimes call marine snow. It is not snow in the cozy winter sense. No one is building a little deep-sea snowman with a carrot nose down there, which is probably for the best. But it is a steady fall of food and material from the upper ocean to the deep. In this way, the trench receives messages from the surface world, slow and fragmentary, sinking through the darkness. Sediments also collect there over long periods. Layer by layer, the seafloor can preserve information about past events, climate, erosion, volcanic activity, earthquakes, landslides, and biological change. The mud may look plain, but it can hold history. Of course, retrieving and interpreting that history is not simple. A core sample from the seafloor is a narrow record, like pulling one long straw from an enormous layered cake and trying to understand the whole dessert. It helps, certainly, but you need many samples from many places, and you need to know how those samples fit into the broader shape of the trench. The deeper we imagine it, the more the trench becomes less like a destination and more like a system. It is a deep place, yes, but it is also a boundary, a hazard zone, a sediment trap, a biological habitat, a geological archive, and a mapping challenge. It is tied to the island above it, the plates beneath it, the water column over it, and the wider Atlantic around it. That is why it cannot be truly explored by one dramatic descent. It must be approached from many directions. Sonar from above, seismic surveys through the crust, samples from the bottom, cameras in the dark, long-term instruments listening for movement, historical records, hazard models, biological surveys. Each one adds a piece. For now, as we drift in thought above that long blue shadow, the most useful thing is to understand the scale of what we're asking. We're not asking why someone has not simply gone down and looked. People have looked. Machines have visited. Ships have mapped. Scientists have studied. We are asking why looking does not easily become knowing. The answer begins with the fact that the Puerto Rico Trench is not a room with a light switch. It is a vast, dark, pressurized landscape at the meeting place of moving plates, hidden under an ocean that makes every measurement expensive and every visit brief. And that is before we even consider what the water itself does to our machines when we try to send them down. The first thing the ocean does, long before we reach the trench floor, is add weight. Not weight in the way we usually imagine it, like a heavy suitcase, a full shopping bag, or a blanket that somehow feels perfect until you try to move your foot. This is weight from every direction at once. Water presses down from above, in from the sides, and around every surface it can touch. It does not need to rush. It does not need to strike. It simply exists, and the deeper we go, the more of it there is. At the surface, we live under pressure already. Air has weight, though we rarely think about it because our bodies are built for it. We move through air so easily that it feels almost like nothing. But it is not nothing. It presses on us all the time and we press back. Step underwater and the pressure begins to change quickly. Just a short swim beneath the surface can make your ears complain. Go a little deeper and your body notices. Go deeper still, and ordinary human comfort leaves the conversation entirely. For every 10 meters or so beneath the ocean surface, the pressure increases by about 1 atmosphere. That means that at 10 meters down, the pressure is roughly double what it is at the surface. At 20 meters, it is roughly triple. This may sound manageable when spoken calmly, but the arithmetic becomes severe very quickly. At 100 meters, the pressure is already far beyond normal human experience. At 1,000 meters, the water is pressing with a force that makes ordinary containers, ordinary electronics, and ordinary human bodies very unhappy. The Puerto Rico Trench reaches many thousands of meters deeper than that. This is why the phrase, "going down there," can be misleading. It sounds like a direction, the same way you might go down a hill, down a staircase, or down to the kitchen because sleep has failed and toast has become an option. But in the deep ocean, going down is not just movement, it is entering a different physical environment. Every meter adds more pressure, every descent asks more from the machine. Every seal, window, cable, battery case, motor housing, camera, light, and scientific instrument must be designed with the weight of the ocean in mind. At great depth, pressure is not one problem among many. It is the problem that touches all the others. It decides what shape a vehicle can be. It decides what materials are safe. It decides how thick the walls must be. It decides what kind of glass can be used, if any. It decides whether a camera housing survives long enough to record a fish, a rock, or 10 minutes of suspended sediment looking deeply unhelpful. It decides whether a tiny flaw becomes a failure. This is one of the reasons deep-sea engineering often favours simple shapes. Spheres are good under pressure because they spread force evenly. Cylinders can work too, but they must be designed carefully. Flat surfaces are more troublesome because pressure can push on them unevenly. A window on a deep-sea vehicle is not just a window. It is a serious engineering decision with a view attached. It must be strong enough to hold back the ocean while still letting someone or something see through it. That is a lot of responsibility for a piece of material that, on land, would mostly be asked to keep out rain and perhaps a nosy pigeon. A deep-sea vehicle also has to contain spaces at normal or near normal pressure if people or delicate electronics are inside. That means the outside of the vehicle may be facing hundreds or even more than 1,000 times surface pressure in the deepest trenches, while the inside remains safe and dry. The difference between inside and outside becomes enormous. The ocean is trying, in its quiet physical way, to make those differences disappear. It wants to push inward. It wants to fill any empty space. It wants balance. The vehicle must politely but firmly disagree for the entire mission. This is why tiny leaks matter so much. On land, a small leak might be annoying. A dripping roof ruins a ceiling. A leaking pipe creates a puddle. A water bottle in a bag commits a minor betrayal against your notebook. In the deep ocean, a leak is not just water arriving where water should not be. It is water arriving under tremendous pressure. It can enter fast, it can damage circuits, crush air-filled spaces, short electronics, ruin sensors, and end a mission before the vehicle has done its work. The deeper the vehicle goes, the less forgiving the ocean becomes. Even equipment that does not carry people must be built for this. Many deep-sea instruments are placed inside pressure housings. Batteries need protection. Computers need protection. Cameras need protection. Lights need protection. Sampling tools must still move under pressure. Motors must operate. Connectors must seal. Cables must handle strain. Nothing can be treated as ordinary just because it looks ordinary at the surface. A switch is not just a switch. A plug is not just a plug. A little rubber seal is not just a little rubber seal. It may be the thin line between useful data and an expensive object having a very bad evening. Then there is the problem of air. Air compresses. Water does not compress nearly as easily. Anything with trapped air inside it can become vulnerable as pressure increases. If the structure around that air cannot resist the force, it may collapse inward. This is why objects from the surface can be crushed in deep water. It is also why deep-sea animals do not carry air-filled spaces in the way surface animals often do. Their bodies are adapted to pressure because they are not fighting the ocean in the same way a machine is. They belong there. Our equipment is visiting, and the ocean can usually tell. A fish living in the deep trench does not need a titanium sphere. It does not need a pressure-rated camera housing or a launch crew. It is made of materials that function under those conditions. Its cells, membranes, proteins, and body structure work in an environment that would ruin most surface life. That does not mean deep-sea animals are invincible. Bring some of them to the surface too quickly, and the change in pressure can harm or kill them. They are adapted to their world, not ours. This is another reminder that exploration is not just about humans surviving the deep. It is also about observing deep life without destroying the conditions that make it possible. For the Puerto Rico Trench, pressure complicates nearly every scientific question. Suppose researchers want to know what animals live on a slope. They need cameras, lights, and perhaps a vehicle that can move carefully. Suppose they want sediment samples. They need corers or scoops that can operate in mud under extreme pressure. Suppose they want to measure chemistry. They need sensors that remain accurate despite cold, pressure, and time. Suppose they want long-term monitoring. They need instruments that can survive for months or years, sitting quietly in darkness while the ocean presses on them every second. Long-term instruments are especially demanding because they cannot simply be watched and adjusted like equipment in a laboratory. On land, if a sensor stops working, someone may be able to walk over, open a box, replace a part, and make a face at the instruction manual. In the deep ocean, if an instrument fails, it may remain failed until a ship returns. That could be months later. It could be longer. A recovery system must work. The batteries must last. The data must be stored safely. The housing must resist corrosion and pressure. The instrument must not sink into soft sediment in an unfortunate position, which is the scientific equivalent of falling asleep during your own presentation. Pressure also affects buoyancy. Vehicles and instruments must be able to descend and return. That sounds obvious, but it is not easy. A submersible or autonomous vehicle needs enough weight to sink, enough buoyancy to rise, and enough control to move as intended. Materials behave differently under pressure. Some compress slightly, some lose buoyancy. Foam used for deep-sea buoyancy is not the kind of foam you find in a sofa cushion, which is good because a sofa cushion at trench depth would have a brief and disappointing career. Deep ocean buoyancy materials must resist compression while remaining light enough to help lift equipment back toward the surface. At these depths, even bringing something back is a serious plan. A sample collected at the bottom must be secured. A vehicle must leave the seafloor. It may need to rise for hours through the water column. The ship must track it. The crew must recover it. Weather must allow safe retrieval. If the sample includes living organisms, the change in pressure and temperature may alter them before scientists can study them. If the sample includes gas-rich sediment or delicate structures, the trip upward may change what was collected. The trench does not only make reaching the bottom difficult, it makes preserving the truth of the bottom difficult too. This is important because the deep ocean is not only a place, it is a set of conditions. A rock brought to the surface remains a rock, more or less. A sediment core may preserve layers, though it can still be disturbed. But an animal, a microbial community, a chemical gradient, or a fluid moving through seafloor cracks may change when removed from pressure. To understand the trench properly, scientists increasingly need measurements made in place. That means instruments must not only survive the pressure, they must work accurately while inside it. The machine has to become a small laboratory that can tolerate the deep. That is a great deal to ask of any machine. It must be strong, but not too heavy. It must be sealed, but still able to move parts. It must carry power, but batteries have limits. It must communicate, but radio waves do not travel well through seawater. It must navigate, but GPS does not work at the bottom because satellite signals do not penetrate the ocean. It must see, but there is no sunlight. It must collect data, but every sensor adds complexity. It must be recoverable, because leaving expensive equipment behind is not usually considered a charming tradition. The pressure is not loud. That may be what makes it so unsettling. In films, danger often announces itself with shaking, alarms, sparks, and someone saying, "That should not be doing that." Deep-sea pressure can be quiet until it is not. A housing may hold perfectly, or it may fail suddenly. The force involved is immense. Engineers test equipment carefully because the deep ocean does not offer many second chances. A design that seems strong in a workshop must be proven under the conditions it will face. Pressure testing is not optional. It is how a machine earns the right to visit. This is one reason human-occupied exploration is so limited. Sending people to great depth requires a pressure vessel strong enough to protect life. It must have life support, communication, controls, emergency systems, and a way back. Every human need adds weight, complexity, and risk. A person needs air, warmth, space, visibility, and safety. A camera does not need to be comfortable. A sensor does not get bored. A robotic vehicle does not become quietly concerned about the number of kilometers of water above its head. For the deepest places, robots are often the more practical visitors. Even robots have limits. Remotely operated vehicles, or ROVs, are connected to ships by cables. Those cables provide power and communication, which is useful, but a long cable in deep water is difficult to manage. It has weight, drag, and movement. Currents can push on it. The ship must hold position. The deeper the vehicle works, the more cable must be deployed, and the more complicated the system becomes. Autonomous underwater vehicles, or AUVs, avoid the cable by operating on their own, but then they must carry their own power, follow pre-planned missions, store their data, and return without constant human control. This is useful, but it also means scientists cannot always react immediately to what the vehicle sees. In the Puerto Rico Trench, this matters because the environment is not just deep, it is varied. A vehicle may need to move over steep terrain. It may pass from softer sediment to exposed rock. It may encounter slopes, cracks, ledges, or areas where navigation becomes difficult. At depth, a small navigation error can mean missing the target area entirely. Without GPS, vehicles rely on other systems, such as inertial navigation, acoustic positioning, and careful mission planning. None of this is impossible, but none of it is simple either. The deeper the mission, the more every uncertainty matters. The ocean's weight also limits how often we can return. If visiting the trench were as easy as hiking to a field site, scientists could build knowledge quickly. They could go often, compare seasons, repeat measurements, fix mistakes, and follow up on surprises. But a deep trench mission requires ships and specialized equipment. Research vessels are expensive to operate. They must be scheduled. Teams must be assembled. Weather must cooperate. Instruments must be ready. If one part of the chain fails, the opportunity may be lost. In that way, pressure creates not only a physical barrier but a practical one. It turns curiosity into logistics. This is why our knowledge of the deep ocean often grows in bursts. An expedition maps a section. Another expedition collects samples. Years later, a new vehicle returns with better cameras. A sensor is deployed. A sediment core is analysed. A model is improved. The picture becomes clearer, but slowly. The Puerto Rico Trench does not reveal itself in one grand unveiling. It gives information in pieces, and the pieces are hard-earned. There is also the issue of scale. The pressure at the deepest parts may be the most dramatic, but the entire descent is a changing environment. A vehicle must pass through layers of water with different temperatures, densities, currents, and chemical properties. The upper ocean is not the same as the middle depths, and the middle depths are not the same as the Hadal zone. The trench begins long before the bottom, in the sense that every layer affects the mission. Sound speed changes with water conditions, which matters for sonar and acoustic communication. Currents can move vehicles off course. Suspended particles can affect visibility. The water column is not empty space, it is part of the challenge. By the time a machine reaches the lower slopes or floor of the trench, it has already survived a long vertical journey. It has passed through darkness, cold and rising pressure. It has carried its own light into a place where sunlight never arrives, and then, once it reaches the bottom, it must work gently enough not to ruin the very thing it came to observe. Thrusters can stir sediment. A manipulator arm can disturb fragile life. A sampling tool can miss or collect too much. A bright light can reveal the scene, but it may also affect animals that live in darkness. Exploration is not just arrival, it is careful behaviour after arrival. That careful behaviour is harder when the vehicle is under pressure, far away, and dependent on systems that can fail. A pilot operating an ROV from a ship must interpret camera views, sonar returns, instrument readings, and the movement of the vehicle. There may be a slight delay. Visibility may be poor. The seafloor may be uneven. The vehicle may need to hover close enough to see, but not so close that it crashes or raises a cloud of mud. It is a slow kind of work, not dramatic in the usual sense, but tense in a very practical way. The ocean does not hurry, and neither can the people studying it. Pressure also shapes the cost of exploration. Strong materials, specialised testing, pressure-rated components, deep-sea cables, ship time, trained crews, and recovery systems are expensive. The deeper you go, the fewer off-the-shelf parts you can use. Everything becomes more specialised. A simple-looking object may have taken years of design, testing, and revision. This does not mean exploration is not worth it. It means that, why have we not explored more, often has a very plain answer. Because each reliable glimpse requires a large amount of money, time, engineering, and coordination. There is a quiet irony in this. The trench is made of earth, water, rock, mud, and life. The same broad ingredients that make many natural places. But to see it, we need some of the most advanced technology humans can build. A crab walking across deep sediment may do so with no equipment at all, while we require a pressure-tested vehicle, a research ship, a navigation system, lights, cameras, computers, and enough paperwork to make even the crab lose interest. The animals are at home. We arrive like nervous guests carrying too many bags. And yet the pressure is not only an obstacle, it is part of what makes the trench scientifically valuable. Life at high pressure teaches us about the limits of biology. Sediments under pressure preserve records in ways we are still learning to read. Fluids moving through deep crust behave under conditions that are hard to reproduce. The trench is not just hard despite the pressure, it is interesting because of the pressure. The very force that keeps us away helps create the environment we want to understand. This is why the Puerto Rico Trench cannot be treated like a simple blank spot waiting to be coloured in. It is not only unmapped space, it is a place where the rules feel different because the physical conditions are different. The water above it becomes a wall, a weight, a filter, and a test. It blocks light, bends sound into the main tool for mapping, crushes weak structures, complicates communication, slows recovery, and makes every visit brief compared with the long life of the trench itself. So when we say the ocean becomes too heavy to hold, we're not speaking as if the water suddenly changes character at one exact line. The change is gradual. Metre by metre, the familiar sea becomes an environment where ordinary human assumptions fail. A plastic bottle, a camera case, a wire, a window, a motor, a person, all must answer the same question. Can you withstand what is above you? In the Puerto Rico Trench, that question is asked with the full weight of the Atlantic, and it is asked continuously. This is where exploration begins to feel less like travel and more like negotiation. We do not conquer the pressure. We design around it. We do not remove the darkness. We carry small lights into it. We do not make the trench easy. We accept that it is not easy, and then build tools that can survive there for a little while. The trench remains itself. We are the ones who must adapt, and our machines become the temporary bodies we use to enter a world where our own bodies cannot go. And even after a machine survives the weight, even after its housings hold, its seals remain tight, its lights switch on, and its cameras open a small window into the dark. The trench still has another way of making exploration difficult. The bottom is not a flat floor waiting beneath the water. It is a landscape shaped by earthquakes, slopes, faults, and slow geological movement, and the ground itself is not always as still as it appears. Before any machine can visit the bottom, before a camera can switch on in the dark, before a sample can be taken from the mud, scientists have to answer a very basic question. What exactly is down there, and where is it? That sounds simple, almost too simple. We are used to maps being available instantly. We open a phone, type a place name, and there it is. Roads, buildings, traffic, shops, photographs, walking directions, and sometimes even a review from a person who gave a sandwich shop 2 stars because the weather was bad. The surface world has become so easy to view that it gives us the impression that mapping is finished. Land feels documented, cities feel visible, mountains have names, trails, and little dotted lines telling us where not to take a rental car. The seafloor is different. The Puerto Rico Trench has been mapped in important ways, but mapping a trench is not the same as understanding it. A map can show the broad shape. It can show where the floor drops, where slopes rise, where ridges run, where basins sit, and where channels may cut through sediment. But the trench is too deep, too large, and too complex to be reduced to one clean image. A map of the deep sea floor is not a window. It is a translation. Sound goes down, echoes come back, computers process those echoes, and slowly a picture is built from returned signals. It is a clever picture, a useful picture, and often a beautiful one, but it is still made from distance. On land, a surveyor can stand on the ground being measured. A geologist can place a hand on a rock. A biologist can kneel beside a plant. A person can walk up a hill and notice that the map was right about the slope, but deeply optimistic about the path. In the Puerto Rico Trench, nearly everything begins from the surface of the sea. The ship floats many kilometres above the target. The bottom is hidden beneath water that blocks light and hides detail, so instead of looking directly, scientists listen. This is what sonar does. A ship sends sound pulses downward into the ocean. Those pulses travel through the water, strike the seafloor, and return as echoes. By measuring how long the sound takes to return, scientists can estimate depth. Repeat that again and again as the ship moves, and a shape begins to appear. Not all at once, but in strips, lines and swaths. The seafloor is built into a map the way a room might be understood by tapping the walls in darkness and listening carefully. It works, but it asks for patience. Deep water makes the process slower and harder. The farther the sound travels, the more the measurement depends on knowing the water itself. Sound does not move through seawater at one constant speed everywhere. Temperature, salinity, and pressure all affect it. A warm layer near the surface, a colder layer below, and changes in salt content can alter the path and speed of sound. That means scientists must measure the water column too. The ocean between the ship and the trench is not empty space. It is part of the measuring instrument, whether it wants that responsibility or not. When a sonar pulse returns, it carries information, but not a full explanation. It tells scientists something about distance, and sometimes something about the texture or hardness of the bottom, depending on the instrument and the data. But sonar alone cannot tell the whole story. A steep return might suggest a cliff, a scarp, or a slope. A smooth region might be mud, sediment, limestone, or something else entirely. A rough patch may be rocks, biological growth, landslide debris, or features formed by faulting. A map can point to questions. It does not answer all of them by itself. This is why the trench still seems to whisper through its maps. The lines and colours show depth, but they also hint at uncertainty. They say, here is a slope, but what is it made of? Here is a ridge, but how did it form? Here is a depression, but is it quiet sediment or a record of old movement? Here is an area that looks smooth, but is it truly smooth, or is the map too coarse to show the smaller details? A map can reveal that something exists and still leave the most interesting questions waiting in the dark. Resolution matters. This is a word that appears often in mapping, and it simply means how fine the detail is. A low-resolution map can show large features but miss small ones. A high-resolution map can show finer structure, but it takes more data, more time, and often more careful surveying. If you look at a whole country from far above, you see coastlines, mountains, and rivers. Move closer, and roads appear. Move closer again, and houses appear. Move closer still, and you may see the garden chair someone promised to put away last autumn. Each level of detail changes what the map can tell you. The same is true underwater. A coarse map of the Puerto Rico Trench may show its general depth and shape. A better map may show steep slopes, cracks, channels, landslide scars, ridges, or small seamounts nearby. A very detailed map may reveal features that matter for geology, biology, and hazards. The problem is that high-resolution mapping of deep-sea floor takes ship time, and ship time is limited. A research vessel cannot map the whole deep ocean by wishing politely at it. It must move line by line, collecting data as it goes. The deeper the water, the broader the sonar footprint can become, and the more care is needed to produce a useful result. Imagine trying to scan the floor of a large dark hall while standing on a balcony far above it. Your flashlight beam spreads, shadows distort, small objects become harder to identify. You may still learn the shape of the room, but if you want to know whether there is a crack in the tile or a coin near the wall, you need to get closer. In the deep ocean, getting closer means sending a vehicle down, and that brings back all the problems of pressure, navigation, power, and recovery. This is one reason ship-based sonar and deep vehicles often work together. A ship can map a broad area from above. That map helps scientists decide where to send a remotely operated vehicle, an autonomous vehicle, a camera system, or a sampling tool. The broad map is the guide. The vehicle provides close detail, but if the broad map is incomplete, scientists may not know where the most important features are. They may miss a fault scarp, a fresh landslide, a steep wall with exposed rock, or a habitat where deep-sea animals gather. Exploration begins with choosing where to look, and choosing where to look requires knowing enough to choose well. This is harder in the Puerto Rico region because the seafloor is not one simple structure. The trench lies within a complicated area shaped by plate motion, faulting, sediment movement, and the long history of the Caribbean margin. To the north is the deeper Atlantic setting. To the south are islands and slopes connected to Puerto Rico and the Virgin Islands. Between them is a seafloor that has been bent and shaped by tectonic forces over a very long time. A map has to represent not just depth, but structure. It must show a landscape that may have formed through several different processes acting together. This is where bathymetry becomes more than a technical word. Bathymetry is the measurement of underwater depth and seafloor shape. In a place like the Puerto Rico Trench, bathymetry is not just useful for navigation. It is a way of reading the seafloor. A sudden step may mark a fault. A broad, smooth area may hold thick sediment. Curved scars may suggest a past submarine landslide. Channels may show where sediment has moved downslope. Ridges may reveal deformation. The shape of the bottom can tell stories, but only if the map is detailed enough and if scientists can compare it with other evidence. Other evidence may include seismic surveys, which send sound energy into the seafloor to image layers beneath it. Surface mapping shows the top. Seismic data can show what is under that top. Sediment cores can provide material from the layers. Rock samples can reveal composition. Earthquake records can show where stress is being released. Together, these tools begin to turn a map into an explanation. Without them, the map is still valuable, but it remains partly silent. The word silent is not quite right, of course, because the ocean is full of sound. Ships, animals, waves, earthquakes, rain, and the movement of the water all create noise. But the seafloor is silent in the sense that it does not explain itself. A feature can be visible in bathymetry and still be ambiguous. A scar on a slope may be old or recent. A channel may be active or abandoned. A ridge may be made of rock, sediment, or a mixture of both. The map whispers because it gives hints without giving everything away. There is also the problem of change. A map is a record of a place at the time it was measured. On land, this is usually fine, unless someone builds a road, cuts down trees, or creates a roundabout that confuses everyone for a decade. Underwater, change can happen suddenly in places affected by earthquakes, slope failures, or sediment flows. A submarine landslide can reshape part of the seafloor. An earthquake can shift features. Sediment can move downslope in dense flows. The deep ocean may look still because we rarely see it changing, but stillness is not the same as permanence. This matters for the Puerto Rico Trench because the region is associated with earthquake and tsunami hazards. To understand those hazards, scientists need maps that are not only detailed but also connected to geological processes. Where are the steep slopes? Where is sediment piled up? Where are possible landslide scars? Where are faults visible at the sea floor? Where might shaking cause material to move? These are not casual questions. They are part of understanding risk for nearby islands and coastal communities. Yet risk mapping cannot be done with one simple pass. A feature that looks like a landslide scar in bathymetry may need closer inspection. A fault may need seismic data. Sediment thickness may need coring or sub-bottom profiling. Repeated surveys may be needed to detect change. A hazard map is built from layers of evidence. The trench gives scientists the outline, but it asks them to keep returning for the details. This is why the phrase "we have a map" can be misleading. There are many kinds of maps. Some are global maps, useful for seeing large features but too coarse for local decisions. Some are regional maps, good for understanding broad structure. Some are high-resolution surveys collected by research ships, which can reveal much more. Some are vehicle-based maps made close to the seafloor, showing fine detail but only over smaller areas. Each kind of map has a job. None of them alone is the complete trench. A global map might show the Puerto Rico Trench clearly as the deepest part of the Atlantic, but it may smooth over smaller features. A ship-based multi-beam map might show important slopes and ridges in much better detail, but it may not cover every connected area. A deep vehicle may map a small patch beautifully, but it cannot cover the whole region quickly. So the trench becomes a patchwork of different resolutions, different dates, different instruments, and different scientific aims. The challenge is to fit those pieces together without pretending they are all equally detailed. This is one of the quieter difficulties of ocean science. The public often sees the final image, a coloured bathymetric map with blues, greens, yellows and reds, and it looks complete. It looks certain. It looks like the seafloor has been revealed. But behind that image are choices, gaps, corrections, interpolation and limits. Interpolation means estimating values between measured points. It is useful and often necessary, but it is still estimation. If an area has sparse data, the map may look smooth not because the seafloor is smooth, but because there are not enough measurements to show otherwise. That can be a little unsettling. A smooth blank on a map may not be a smooth blank in reality. It may be a place where the data is thin. The trench, in that sense, has two landscapes. One is the real landscape of rock, mud, slopes, faults and life. The other is the data landscape, made of what we have measured well, what we have measured poorly, and what we have not measured at all. Exploration is the process of making the data landscape catch up with the real one. The Puerto Rico region has seen important mapping work, and those efforts have improved what scientists know. Modern multi-beam sonar can reveal features that older methods missed. Expeditions can fill gaps and create better maps for science, resource management, and hazard planning. But filling gaps is not the same as finishing the story. A mapped area can still require ground truth. Ground truth means checking what the remote data suggests by using direct observations or samples. It is a wonderfully practical phrase. The map says one thing. The ground, or in this case the seafloor, gets the final vote. To collect ground truth in a trench, scientists may lower cameras, use ROVs, deploy autonomous vehicles or take samples. Each method has limits. A camera tow may cover a path but not a wide area. An ROV can inspect closely but slowly. An AUV can survey efficiently, but may not make real-time decisions the way a human pilot can. A sediment corer collects material from one narrow point. A dredge can bring up rocks but may disturb context. Every tool is useful, and every tool leaves something out. This makes deep-sea mapping feel less like drawing a final picture and more like assembling a careful argument. The sonar suggests this. The images support that. The samples show this material. The seismic data suggests these layers. The earthquake records point to this structure. The biological observations show these habitats. The argument becomes stronger as more evidence agrees. But in a place as deep and complicated as the Puerto Rico Trench, the argument is always open to improvement. There is another reason maps whisper. They hide time inside shape. A trench feature is not only a form in space. It is the result of events and processes over time. A slope may have been steepened slowly by tectonic movement. A basin may have filled gradually with sediment. A scarp may have formed suddenly during an earthquake. A landslide scar may record a past collapse. A channel may mark repeated sediment flows. When scientists look at bathymetry, they're not only asking what is where, they're asking what happened here. That question is harder. Shape alone can suggest a history, but it rarely proves it. Two different processes can create similar-looking features. A scar may resemble another scar. A ridge may have more than one possible origin. A smooth surface may be new sediment or old material hidden beneath a covering. The map gives the first clue, not the final answer. To understand the trench as a place with a history, scientists need to combine mapping with geology. This is especially important when thinking about underwater landslides. A large slope failure under the sea can move huge amounts of material. It can also disturb water and in some cases contribute to tsunami hazards. Not every slope is dangerous, and not every landslide produces a major wave. But the possibility is serious enough that scientists pay close attention to slope shape and sediment stability. In the Puerto Rico region, where earthquakes are part of the tectonic setting, mapping steep and unstable areas matters. But the trench does not make even this easy. A landslide scar may be partly buried. Sediment may cover older features. New deposits may smooth the surface. Deep currents may reshape fine material. The deeper the feature, the harder it can be to inspect. A map may show a curved headwall or hummocky terrain, and scientists may suspect a past slide. But to know more, they need closer data, samples, and sometimes repeat surveys. The map whispers, something happened, but does not always say when, how, or how large. Mapping also affects biology. Deep-sea animals do not live randomly. They respond to seafloor shape, sediment type, currents, food supply, hard surfaces, and chemical conditions. A steep rocky wall may host different life than a flat muddy basin. A ridge may alter currents and bring food. A depression may collect organic material. If scientists want to understand life in the Puerto Rico Trench, they need habitat maps. That means maps detailed enough to show the difference between rock, mud, slope, channel and ledge. This is where broad maps and close observations meet again. Bathymetry can suggest where habitats may be. Images and samples confirm what lives there. Without the map, researchers may not know where to look. Without the images, the map remains biological guesswork. A smooth patch of sediment might be empty, or it might hold tracks, burrows, microbes or animals that move slowly and do not appear clearly in low-resolution surveys. A rocky area may be too small to show on a coarse map but large enough to matter for life. The trench is therefore not only a mapping challenge for geology, it is a mapping challenge for ecology, hazards, navigation, and even basic curiosity. Each question needs a different kind of detail. A navigator may need one map, a geologist may need another, a biologist may need a third, a hazard specialist may need all of them, plus earthquake records and models. The same seafloor can be mapped many times for different reasons, and each time it may reveal something new. This can make exploration seem slow, but slow is not the same as unproductive. In deep ocean science, progress often comes from improving resolution. A first map says, there is a trench here. A better map says, this side is steeper than that side. A better one shows ridges and scarps. A better one reveals possible slide deposits. A vehicle survey shows the rocks, mud and animals. A sample shows age and composition. A repeat survey may show change. Knowledge grows by layers, not by a single dramatic reveal. There is a useful lesson in that for how we think about the ocean. We often want mysteries to end in one clear answer. What is down there? Why can we not explore it? What does the map show? But the Puerto Rico Trench does not provide one answer, because it is not one question. It is a whole set of questions stacked on top of each other. How deep is it? What is its shape? What made that shape? How old are its features? Where are the active faults? Where are the unstable slopes? What lives there? How does material move through it? How does it connect to hazards above? What have we missed because our maps are not fine enough? Each of those questions has a different scale. Some are answered in kilometres, some in metres, some in centimetres, some in time spans of millions of years, some in sudden seconds during an earthquake. A single map cannot hold all those scales perfectly. So scientists keep making better maps and asking sharper questions. There is also something very human about the way maps shape imagination. A blank area can feel empty, even when it is not. A smooth line can feel simple, even when the real place is rough. A named feature can feel understood, even when it has barely been visited. This is why maps can be both useful and misleading. They give us confidence, but sometimes too much. They help us think, but they can also make unknown places look more settled than they are. The Puerto Rico Trench has a name, a measured depth, and a place on maps. That can make it seem finished as a subject, as if the main fact has already been collected. Deepest part of the Atlantic, north of Puerto Rico. Very deep. There we are. Put the kettle on. But those facts are only the doorway. The real trench is a landscape with structure, history, hazards, life, and change. The map shows us where the doorway is. It does not take us through every room. and some of those rooms are still dimly drawn. Even when a region has been mapped by modern systems, the quality can vary from place to place. Some areas may have excellent coverage, others may be older, lower resolution, or partly inferred. New expeditions can reveal features that were not clear before. They can correct earlier interpretations. They can show that a slope is more complex, a basin deeper, a ridge sharper, or a habitat more varied than expected. A map is not an ending. It is a working document, and the ocean keeps reminding us not to treat it as final. This is one reason global efforts to map the seafloor matter. The ocean covers most of the planet, yet much of its floor still lacks modern high-resolution mapping. That fact can feel surprising in an age of satellites, but satellites cannot simply see through water. They can help estimate broad seafloor shape using gravity effects on the sea surface, but that is not the same as direct sonar mapping. To know the seafloor well, ships and underwater systems still have to collect data. The modern world has not escaped the need to go there, slowly, line by line. For the Puerto Rico Trench, better mapping is not just about filling in a beautiful image. It can guide where to place sensors. It can identify areas for biological surveys. It can help model tsunami hazards. It can show possible landslide scars. It can help scientists understand how the plate boundary is shaped. It can support decisions about future expeditions. A better map makes every later question more precise, but even the best map cannot remove the trench's basic difficulty. Once the map has pointed to a target, something still has to go there. A vehicle must descend, a sample must be collected, an instrument must be placed, a camera must see. The map can whisper where to look, but the ocean still stands between the ship and the bottom. The trench remains far below, under pressure, cold, darkness, and a water column thick enough to turn every plan into engineering. So when we imagine the Puerto Rico Trench on a map, perhaps we should not picture a finished line. We should picture a conversation. The map says, here is the deep axis, here are the slopes, here are the ridges, here are the places that look smooth, here are the areas where the data is strong, and here are the places where we need more. Then the scientist answers with a new survey, a new dive, a new instrument, or a new model. The trench replies with more detail, more uncertainty, and sometimes a feature no one expected. That is why the trench still feels partly out of reach. Not because it is absent from maps, but because maps are only the beginning of knowing it. The lines and colours tell us where the seafloor falls away, but not everything about why it fell, how it moves, what lives there, or what may happen next. To learn those things, we have to move from the map into the restless ground beneath it, where the deep Atlantic floor is shaped by forces that do not care whether our surveys are complete. To learn those things, we have to move from the map into the restless ground beneath it, where the deep Atlantic floor is shaped by forces that do not care whether our surveys are complete. The seafloor can look still on a map. It sits there in shades of blue and purple, marked by depth lines, slopes, ridges, and long dark depressions. A map gives it a frozen quality, as if the whole place has agreed to hold still while we study it. But that is partly an illusion. The Puerto Rico Trench is not a quiet dent in the ocean floor. It is part of a tectonic boundary, and tectonic boundaries are places where the Earth keeps unfinished business. The land around Puerto Rico may feel solid underfoot. A street, a house, a harbour wall, a road leading uphill, all of it seems stable in the ordinary daily sense. You can put down a chair and expect it to remain where it is, unless someone moves it or the dog develops a sudden interest in furniture. But below that ordinary stability, the crust of the Earth is divided into enormous plates. These plates move slowly, but they do move. They press, slide, bend, and grind past one another over time. Most days, nothing noticeable happens. Then stress that has built quietly for years, decades, or longer is released in seconds. That release is what we feel as an earthquake. Near the Puerto Rico Trench, the North American plate and the Caribbean plate meet in a complicated way. It is not a simple head-on collision. It is not one plate neatly diving under another in the clean, tidy manner of a school diagram where all the arrows behave themselves. The motion in this region includes sideways movement, compression, bending, and areas where the crust is being pulled, tilted, or broken by faults. The result is a seafloor that carries the marks of long-term strain. This is one reason the trench is so difficult to understand. A stable deep basin would already be hard to explore because of pressure, darkness, and distance. But a deep basin inside an active tectonic setting is harder still. Scientists are not only trying to map shape, they're trying to understand movement. They want to know where faults are, how they connect, how often they slip, how much stress they may hold, where the seafloor is steep enough to fail, and how all of this might affect nearby islands. The problem is that the seafloor does not explain its intentions. A fault can sit quietly for a very long time. It can appear as a line, a step, a scarp, or a subtle break in the seafloor. It may be visible in bathymetry or hidden under sediment. It may be active now, or it may be an older feature left behind by past movement. It may slip in small earthquakes, or it may be part of a system capable of larger movement. To understand it, scientists need more than a map. They need earthquake records, seismic imaging, sediment layers, repeated measurements, and sometimes instruments placed on or near the bottom. That last part is where the trench becomes especially difficult. On land, monitoring faults can be demanding, but at least the instruments can be reached. Seismometers can be placed in the ground. GPS stations can track slow motion. Researchers can visit sites, repair equipment, download data, replace batteries, and check whether a goat has chewed something important. Under the deep ocean, everything is harder. Instruments must survive pressure, corrosion, darkness, and long isolation. They must be deployed from ships, positioned carefully, left to record and recovered later. If something fails, no one can simply drive out and fix it. This matters because earthquakes do not wait for our instruments to be ready. The Earth does not check the research schedule before moving. A fault may slip while no nearby seafloor instrument is in place. A small quake may be recorded only by distant stations, giving scientists useful but incomplete information. A large event may reveal a great deal, but also arrive with danger. Monitoring an underwater tectonic region is a little like listening through a wall to a machine in another room. You can hear enough to know it is working, but not always enough to see which part moved. The Puerto Rico region has a long history of earthquakes and tsunami concerns. The reason is not mysterious. It sits near active plate boundaries and steep underwater terrain. When the seafloor shifts suddenly during an earthquake, it can disturb the water above it. If enough water is displaced in the right way, a tsunami can form. Tsunamis are not ordinary waves in the way people picture beach waves curling toward the sand. In the open ocean, they can be long, fast-moving waves with energy spread through the water column. They may pass under a ship with little drama, then become dangerous as they enter shallower water near shore. That is why the shape of the seafloor matters. The trench, the slopes, the nearby basins, the island margins, and the underwater platforms can all affect how energy moves. A tsunami does not travel through a blank space. It travels over a shaped ocean floor. Depth changes its speed. Slopes and basins can influence its behaviour. Coastlines determine how it comes ashore. To model that properly, scientists need accurate bathymetry, but they also need to understand what kind of seafloor movement might create the wave in the first place. Earthquakes are one possible source. Underwater landslides are another. A submarine landslide sounds almost familiar at first. On land, we know what a landslide is. A slope gives way. Rock, soil, and debris move downhill. Roads can be blocked. Houses can be damaged. Someone on the evening news stands beside a pile of mud looking damp and serious. Underwater, the same basic idea can happen, but the scale and setting are different. A slope beneath the sea can fail. blocks of material can move downslope. Sediment can rush into deeper water. If that movement displaces enough water, it may contribute to tsunami generation. The northern margin of Puerto Rico has steep underwater slopes and evidence of past slope failures. Some of these failures are large enough to matter scientifically and for hazard studies. Their shapes can be seen in detailed seafloor maps as curved scars, collapsed sections, or debris fields. But knowing that a slope failed in the past is not the same as knowing when it failed, how fast it moved, what triggered it, or whether similar slopes could fail again. Those questions require detailed work, and detailed work in deep water is slow. A slope can look peaceful for thousands of years before it fails, or it can fail in smaller pieces, or it can be partly stabilized by the material it contains, or it can be weakened by earthquakes, sediment loading, fluids moving through the seafloor, or the structure of the rock itself. This is not the kind of thing that can be judged by a quick glance. Even on land, slope stability is complicated. Underwater, in darkness, under pressure, on terrain that may be kilometers below the ship, it becomes even more demanding. Sediment plays an important role here. Over time, material from land, marine life, and the upper ocean settles onto the seafloor. It may collect on slopes and in basins. Some layers are fine and soft. Others may be denser or cemented. Some areas may include carbonate material from platforms north of Puerto Rico and the Virgin Islands. Some may include debris from earlier failures. Layers can tilt, compact, weaken, or be disturbed by shaking. A slope is not just a surface. It has internal structure, and that structure matters. To understand that internal structure, scientists use seismic methods, cores, and samples. Seismic surveys can image layers beneath the bottom by sending sound energy into the seafloor and recording reflections. Sediment cores can bring up long tubes of material, preserving layers that can be dated and studied. Rock samples can reveal strength and composition. But each method has limits. A seismic profile is like a slice through the ground, not the whole cake. A core is one narrow point. A sample may not represent the entire slope. To understand a large underwater margin, researchers need many pieces of evidence. That is why the seafloor refuses to sit still in two different ways. Physically, it can move during earthquakes, creep slowly, or fail on slopes. Scientifically, it refuses to sit still because every answer changes the question. A map reveals a scar. The scar suggests a landslide. A core may show disturbed sediment. The disturbed layer needs a date. The date must be compared with earthquake history. The slope shape must be modelled. The model depends on material strength. Material strength depends on samples. The samples depend on where the ship can go and what equipment can reach. The chain continues, patient and slightly exhausting, like trying to understand a family argument by interviewing one cousin every 7 years. Earthquakes themselves are also not simple points on a map. When a quake is recorded, it is usually given a location, depth, and magnitude. That is useful, but the real rupture may involve a fault plane, direction of movement, stress changes, and connection to surrounding structures. In a complex plate boundary zone, different faults may move in different ways. Some may slide sideways, some may involve compression, some may involve extension. Some earthquakes may occur shallowly near the crust, others may occur deeper within a descending slab. The pattern matters because it tells scientists how the plates are interacting. The Puerto Rico Trench region is especially interesting because it includes unusually deep seafloor, strong gravity anomalies, tilted platforms, active faulting, and nearby islands where hazards matter. A gravity anomaly means that measurements of Earth's gravitational field differ from what would be expected. In this region, the very negative gravity anomaly has drawn scientific attention because it suggests unusual mass distribution and dynamic forces in the crust and upper mantle. That may sound like the Earth being needlessly mysterious, which, to be fair, it often is. but it matters because it points to deeper processes shaping the trench and surrounding region. The tilted carbonate platform north of Puerto Rico is another clue. Carbonate platforms usually form in shallow marine environments, building from the remains of organisms and chemical processes in warm, shallow seas. If such layers are now tilted and connected to a deep trench setting, that tells scientists the region has been deformed. It is a visible sign, in the geology, that the crust has not simply remained flat and quiet. It has been moved and bent over time. These clues make the trench more than a deep line. They make it part of a larger tectonic puzzle. Why is the trench so deep? How does the plate boundary accommodate motion? How are stresses distributed? What parts of the system are locked, slipping, bending, or breaking? Where are the main hazards? How do submarine landslides fit into the story? These are not questions a single dive can answer. A remotely operated vehicle might see a fault scarp, a cracked rock face, a muddy slope, or a place where animals have colonized exposed hard ground. That is valuable. But tectonic activity often happens at scales larger and deeper than the vehicle's camera view. A camera may show the surface expression of a fault, but not the full structure beneath it. A sample may show material from one spot, but not how the whole slope is connected. A seismometer may record shaking, but a network is needed to locate and interpret events well. The trench requires both close attention and large-scale context. There is also the problem of time. Human expeditions last days or weeks. Tectonic systems operate across years, centuries, thousands of years, and millions of years. An earthquake may happen in seconds, but the stress leading to it may build for a very long time. A landslide may occur suddenly, but the slope may have been prepared by slow sediment accumulation, earlier shaking, weak layers, and gradual deformation. A research mission captures a window. The trench keeps the rest of the calendar. That is why long-term monitoring is so valuable and so difficult. Scientists want to know not just what the seafloor looks like, but how it behaves through time. Ocean bottom seismometers can help detect earthquakes closer to their sources. Pressure sensors can detect changes in water height that may relate to tsunamis. Geodetic instruments on the seafloor can help measure crustal movement, though these systems are technically challenging. Repeated bathymetric surveys can reveal changes in seafloor shape after major events. Each approach helps, but each requires investment, recovery, and maintenance. The deep ocean is not kind to maintenance. Salt water corrodes, pressure stresses, currents tug, biological growth can interfere, batteries run down, acoustic releases may fail, a sensor placed on soft sediment may tilt, a cable may be damaged, a mooring may move. If an instrument is lost, the data may be lost with it. It is hard enough to listen to a fault from land. Listening from the bottom of the ocean is a more serious commitment. This makes hazard science around the trench both necessary and incomplete. Scientists can identify sources, model scenarios, and study past events, but uncertainty remains. It is not uncertainty from carelessness. It is uncertainty from the limits of observation in a difficult environment. The question is not whether the region matters. It does. The question is how to keep improving the evidence so communities can prepare without pretending the deep seafloor is fully understood. Preparation matters because people live nearby. Puerto Rico and the US Virgin Islands are not geological footnotes. They are homes. A tsunami warning is not an academic exercise for the people who may need to move inland or to higher ground. Earthquake readiness is not a theoretical issue for buildings, roads, hospitals, schools, ports, and families. When scientists study the trench, they are not merely satisfying curiosity about a dark place under the Atlantic. They are improving the information that helps real communities make better plans. At the same time, it is important not to make the trench sound like a monster waiting in the dark. Natural hazards are serious, but they are not villains. The Earth is not plotting. It is moving according to physical processes that have shaped the planet for billions of years. The same plate movement that creates earthquakes also creates islands, mountains, ocean basins, and the dynamic surface that makes Earth what it is. The problem for humans is not that Earth changes. The problem is that we build lives in places where change sometimes arrives suddenly. The Puerto Rico Trench is one of those reminders. It shows that the boundary between land and sea is not just a coastline. The real boundary may continue offshore beneath deep water, along faults and slopes we cannot see from the beach. A calm day at the surface may hide a complicated tectonic setting below. The water may be blue, the sky clear, the boat steady, and still the geological system beneath them is part of a long ongoing adjustment. That hidden activity also affects exploration directly. A steep slope may be scientifically interesting, but risky for a vehicle working close to it. Loose sediment can be stirred by thrusters, reducing visibility. Blocks from past landslides can create uneven terrain. Fault scarps can make navigation harder. If scientists want to place instruments, they must choose sites that are useful but stable enough. If they want samples, they must avoid areas where the vehicle might become stuck or where the tool cannot work properly. The seafloor is not a flat laboratory bench. It is rough, sloped, and in places uncertain. Even the act of interpreting what is seen can be tricky. A pile of broken blocks might be landslide debris, or it might be material exposed by faulting. A smooth, muddy area might be quiet deposition. Or it might cover older disrupted terrain. A crack may be tectonic, or it may be related to sediment settling. A feature can look obvious until another dataset complicates it, which is very considerate of nature if the goal is to keep scientists employed. Earthquake shaking can also disturb the seafloor in subtle ways. Fine sediment may be resuspended. Weak layers may deform. Small failures may occur on slopes. Turbidity currents, which are dense flows of sediment-laden water, can move downslope and carry material into deeper basins. These flows can travel far and reshape the seafloor. They can also damage seafloor cables, which is one reason the deep ocean occasionally reminds modern communication systems that the planet was not designed around broadband convenience. In a trench, sediment flows may end up in the deepest parts, carrying material from shallower slopes into the basin. That means the trench floor can act as a collector of events. A layer in the mud may represent a storm-driven process, an earthquake-triggered landslide, a long period of quiet settling, or some combination. Reading that record is possible, but not simple. Scientists must distinguish one kind of layer from another. They must date the material. They must compare it with known earthquakes, tsunami deposits, and regional geology. The seafloor is a record, but it does not come with captions. This is another reason true exploration takes so long. A dramatic video from the trench may be compelling, but the deeper understanding often comes later, in laboratories, data centers, and careful comparisons. A core is collected in one moment, but it may be studied for years. A map is made during an expedition, but its features may be interpreted and reinterpreted as new data arrive. An earthquake catalogue improves as more instruments are added. A hazard model changes when bathymetry improves. Exploration continues long after the ship has returned to port. There is something oddly comforting in that slow process. It means knowledge does not depend on one perfect mission. It grows through repeated effort. One team maps, another samples, another models, another installs instruments, another studies old deposits on land that may preserve evidence of past tsunamis. The trench is too large and complicated for one set of hands, so it becomes a shared scientific project across years and institutions. But shared work does not remove the central difficulty. The seafloor around the Puerto Rico Trench is active, steep, deep, and partly hidden. It refuses to be reduced to a simple line on a map. It is a place where the ground can move without warning, where slopes can carry the memory of old collapses, where the boundary between plates is not one clean seam, and where the hazards above depend on structures below. To truly explore it, we must understand not just where the bottom is, but what it is doing. That is a much harder task. A depth measurement tells us how far down the seafloor lies. A map tells us its shape. A fault study tells us where the crust may break. A landslide study tells us where slopes have failed. A seismometer tells us when the ground shakes. A pressure sensor tells us how the ocean responds. But the trench asks for all of these at once, connected carefully without rushing to a tidy conclusion. It asks scientists to treat the bottom of the Atlantic not as a static surface, but as a working part of Earth's machinery. And once we accept that the seafloor is not still, the challenge of visiting it becomes even clearer. The machines we send into the trench must not only survive pressure and darkness, they must navigate rough terrain, hover over slopes, avoid stirring sediment, collect samples from unstable ground, and operate in a place where the landscape itself may have been shaped by sudden violence. The trench is not merely deep. It is deep and uneven, deep and active, deep and tied to hazards that reach the world above. That brings us to the machines themselves, those careful, pressure-tested visitors we lower into the dark with lights, cameras, arms, batteries, sensors, and the quiet hope that they will come back. That brings us to the machines themselves, those careful, pressure-tested visitors we lower into the dark with lights, cameras, arms, batteries, sensors, and the quiet hope that they will come back. It is worth pausing for a moment to appreciate how strange these machines really are. On land, a robot can roll across a floor, fly through the air, climb a wall, inspect a pipe, or bump into a chair with all the dignity of a confused shopping trolley. It can use cameras, GPS, wireless signals, and sometimes a helpful person nearby with a laptop and a concerned expression. In the deep ocean, most of those comforts disappear. A robot sent toward the Puerto Rico Trench cannot rely on sunlight, cannot use GPS once it is underwater, cannot call home through ordinary radio, cannot easily be repaired, and cannot ignore the pressure pressing on every part of its body. A deep-sea machine has to be more than clever. It has to be patient, sealed, strong, balanced, visible in darkness, able to move without stirring up too much sediment, able to collect data without getting lost, and able to return to the surface after doing all of that under conditions that would ruin most ordinary equipment very quickly. It is less like sending a camera into a room and more like sending a small laboratory through a very cold, very dark, very heavy column of water while the surface ship waits above like a nervous parent at a school play. There are a few main kinds of machines used for deep ocean exploration. Remotely operated vehicles, often called ROVs, are attached to a surface ship by a tether. Through that tether they can receive power, send video, carry commands, and let pilots on the ship control them in real time. This is a wonderful advantage because it means scientists can see what the vehicle sees as it happens. They can decide to stop, move closer, collect a sample, inspect a rock, follow an animal, or avoid doing something deeply unwise such as driving into a wall of mud because the camera view briefly looked more interesting than it was. But the tether is also a problem. In shallow water, a cable is manageable. In very deep water, it becomes part of the expedition's main challenge. The cable may stretch for kilometers. It has weight. It catches currents. It must be handled by winches and shipboard systems. The ship must maintain position above the working area. If the ship moves too much, the tether moves too. If currents push the cable, the vehicle may feel that pull. If the vehicle is working near steep terrain, the team has to think about where the cable is, where the vehicle is, and where the seafloor rises. A tether gives life to the robot, but it also gives the robot a long tail that can get it into trouble. This becomes especially important near a trench. The Puerto Rico Trench is not a swimming pool with a flat bottom and helpful lane markings. It includes steep slopes, uneven terrain, sedimented areas, and geological features that may be difficult to judge through a camera. A tethered vehicle working near a steep slope has to be handled carefully. The pilots must keep the vehicle close enough to see and sample, but far enough away to avoid collision. They must watch altitude, speed, cable tension, thruster output, and the surrounding terrain. A small movement may look simple from the control room, but in deep water, with the machine far below and the cable hanging through the ocean, every movement is part of a larger system. ROVs are powerful because they allow human decision-making to reach the seafloor without sending the human body down with it. They can carry high-definition cameras, bright lights, sonar, sampling boxes, manipulator arms, and sensors for temperature, salinity, pressure, chemistry, and other measurements. Some can pick up rocks, scoop sediment, collect animals, deploy instruments, or inspect features in detail. They can hover, turn, and move slowly over the bottom like cautious metal insects. But every tool adds complexity. A manipulator arm can collect a sample, but it must work under pressure. A camera can see, but it must be protected. A light can reveal the scene, but it uses power and illuminates only a limited area. A sensor can measure, but it must be calibrated and survive the descent. Then there are autonomous underwater vehicles, or AUVs. These are untethered machines that can travel through the ocean on their own. They are useful for mapping because they can follow planned survey lines, fly closer to the seafloor than a surface ship can, and collect detailed data over a specific area. Without a tether, they are not pulled by a cable and can move more freely. That sounds ideal, and in many ways it is. But freedom comes with a different set of worries. An AUV must carry its own power. It must make decisions based on programming and sensors. It usually cannot stream full video and data back to the ship in the same simple way an ROV can through a tether. It stores much of its information until it returns. In other words, it goes off into the dark with a to-do list, and everyone on the ship has to trust that it understood the assignment. That trust is not blind. These vehicles are carefully engineered and tested. They use navigation systems, depth sensors, sonar, inertial measurements, Doppler velocity logs, acoustic signals, and mission planning to know where they are and where they should go. But underwater navigation is still harder than navigation in air. GPS signals from satellites do not work properly once a vehicle is submerged. A phone can tell you where you are on a city street because it talks to satellites overhead. An AUV under thousands of meters of seawater cannot do that. It has to estimate its position using other tools, and estimates can drift over time. In a flat open area, a small error may not matter much. Near steep slopes or narrow targets, it matters more. If the vehicle is supposed to map a particular scarp, channel, or suspected landslide area, drifting off course can mean missing the feature. If it flies too low, it risks collision. If it flies too high, the data may lose detail. If the seafloor rises unexpectedly, the vehicle must respond. If the terrain drops away, the vehicle must adjust. The trench is not a polite surface. It does not hold still in a convenient shape, because a mission plan was written nicely. Autonomy helps, but it does not remove uncertainty. AUVs can be programmed to follow the seafloor at a set altitude, avoid obstacles or adjust their route. But the deeper and rougher the environment, the more the vehicle must handle on its own. That requires sensors, computing power, and cautious planning. It also requires enough battery life to complete the mission and return. Batteries are a central limitation. A tethered ROV can receive power from the ship. An AUV must bring its own. Every sensor, thruster, light, computer, and acoustic system uses energy. The vehicle must save enough power not only to explore but to come back. A machine that collects beautiful data but does not return is not quite the success anyone had in mind. The return is not a small detail. AUVs usually need to rise to the surface after their mission. The ship must locate them, recover them, and download the data. This may sound straightforward, but the ocean surface is not always calm. A vehicle may surface far from the ship if currents have moved it. Weather may make recovery difficult. The machine may need to be lifted aboard safely. After hours or days underwater, the entire success of the mission may depend on a final recovery operation that takes place in waves, wind, and the kind of deck conditions that make coffee a risky liquid. There's also the third category, human-occupied vehicles. These are submersibles built to carry people into the deep. They are extraordinary machines, and there is something powerful about human eyes looking directly through a viewport at the deep sea floor. A person can notice context, make decisions, react to surprises, and feel the scale of the place in a way that remote viewing cannot fully match. But sending people down requires a pressure vessel, life support, emergency systems, communication, controls, and a very high standard of safety. It adds human vulnerability to an environment already difficult for machines. For the deepest trenches, this makes human dives rare, expensive, and limited. Most of the time, robots are the practical choice. They can go where we cannot. They can stay focused without getting cold, scared, tired, or suddenly remembering they left the oven on. But robots still struggle because they are not truly at home. Everything about them is a compromise between strength, weight, power, mobility, cost, data quality, and recoverability. Take lights, for example. The deep trench is dark. A camera without light sees nothing useful, so vehicles carry bright lamps. But light behaves differently in water than it does in air. It scatters. Particles in the water reflect it back. In sediment-rich areas, thrusters can raise clouds from the bottom, and suddenly the camera is looking into a fog of disturbed mud. The vehicle may have excellent cameras and powerful lights, but if it has stirred the seafloor too much, the view becomes a glowing brown haze. It is the deep-sea version of trying to clean a dusty shelf while shining a torch directly into the dust, and then wondering why the universe has become soup. This is a constant issue when working near soft sediment. The Puerto Rico Trench and its surrounding slopes include areas where fine material has settled over time. A vehicle needs thrusters to move and hold position. Those thrusters push water. That moving water can disturb sediment. If the vehicle gets too close, visibility drops. If it stays too far away, fine details are harder to see. Pilots must balance stability with gentleness. They have to fly a heavy machine in darkness without making the scene vanish. Sampling adds another layer of difficulty. A manipulator arm may try to pick up a rock, place a sediment core, collect an animal, or retrieve a sensor. This requires precision. On land, a scientist can use both hands, adjust their grip, lean closer, and perhaps say something unprintable if a sample breaks. An ROV manipulator is controlled from far above through screens and joysticks. The pilot sees through cameras with limited viewpoints. Depth perception can be tricky. The vehicle may drift. The target may be fragile. The bottom may be sloped. The arm may disturb sediment. A task that would take 5 seconds on land can take many careful minutes underwater, and sometimes the deep ocean simply refuses to cooperate. A rock may be too large, sediment may be too soft, a biological specimen may be delicate and damaged by collection. A tool may not close properly around an object. A sample container may fill with the wrong material. The vehicle may need to back away because the terrain is unsafe. Science in the deep sea involves a great deal of patience, and patience is easier to recommend than to practice when an expensive robot is hovering above the one sample everyone wants. Communication is another challenge. Radio waves do not travel well through seawater, so the usual methods we use for wireless communication are not useful at depth. Tethered ROVs solve this with a physical connection to the ship. AUVs may use acoustic communication, sending sound signals through the water. Acoustic communication can work, but it is slower and more limited than the internet connections we use on land. It can be affected by distance, noise, water conditions, and the geometry of the environment. Sending complex data through the ocean is not like streaming a film at home. It is more like passing short notes across a very large echoing room, while several whales, ships, currents, and bits of machinery all have opinions. This affects how exploration happens. If scientists are controlling an ROV, they can watch live video and respond. If an AUV is running a mission, they may not know exactly what it found until it surfaces. If it sees something unexpected, it may not be able to stop and investigate unless it was programmed with that ability. Newer systems are improving, but autonomy in the deep ocean is still a hard problem, because the environment is difficult to predict and communication is limited. Navigation and communication together create a kind of loneliness for the machine. Once it is far below the ship, especially if it is untethered, it is separated from the world of easy correction. It must keep track of itself. It must follow a plan. It must avoid hazards. It must collect useful data. It must return. The machine is not conscious, of course, but the mission can feel lonely from the surface because people have to wait. They watch estimates, signals, timings, and recovery windows. The vehicle is somewhere in the dark, doing its work, and the ocean is between it and everyone who cares about the result. The cold matters too. Deep ocean water is usually cold, often near freezing. Cold affects batteries, electronics, materials, lubricants, and mechanical parts. Engineers must select components that can function reliably. A moving part that works well in a warm lab may behave differently in cold seawater under pressure. Seals can stiffen, materials can contract, batteries can lose performance. Electronics must be protected not only from water, but from the full range of conditions they will experience. A deep-sea vehicle is not just built for depth, it is built for a journey through changing layers of the ocean. Salt water is another quiet enemy. It corrodes, it gets into places, it damages metals and connections. Even equipment that survives a deep mission must be cleaned, inspected, and maintained after recovery. The ocean is very good at turning shiny engineering into maintenance paperwork. Connectors, frames, fasteners, housings, and exposed surfaces all have to be chosen and protected carefully. Corrosion does not need to be dramatic to be expensive. It just needs time, salt, and opportunity. Then there is the problem of reliability. Deep-sea missions are hard to repeat casually. If a land robot fails during a test, someone can walk over and pick it up. If a deep vehicle has a serious problem at thousands of meters, recovery may be difficult or impossible. Engineers design redundancy where they can. They test systems repeatedly. They plan emergency ascent procedures. They think about what happens if a thruster fails, if a sensor gives bad data, if the battery runs low, if the vehicle loses communication, if a release mechanism does not trigger, if the weather changes during recovery, or if the vehicle becomes tangled. This is not pessimism. It is good engineering. The deep sea rewards people who imagine problems before the ocean does. Every mission plan contains a quiet list of things that must go right. Launch must go right. Descent must go right. Navigation must go right. Data collection must go right. Sampling must go right. Ascent must go right. Recovery must go right. Data transfer must go right. When all of these happen, the result may look smooth to an audience watching a clean video clip, but behind that clip is a chain of success with many links. The Puerto Rico Trench adds its own demands because of depth and terrain. A vehicle working in or near the trench may need to descend for hours before reaching the target. That time is part of the mission. It uses resources. It limits how long the vehicle can work near the bottom. If a dive window is 12 hours and several of those hours are spent descending and ascending, the time available for actual seafloor work becomes precious. The deeper the target, the more each minute at the bottom matters. This affects scientific choices. Researchers may have to prioritize. Do they spend time mapping a slope, collecting a rock, taking a sediment core, filming a biological community, deploying a sensor, or inspecting a suspected fault? A vehicle may be capable of many tasks, but a mission cannot do everything. The trench forces decisions. Curiosity may be wide, but dive time is narrow. The instruments themselves also have limits. Sonar can map, but resolution depends on altitude and system design. Cameras can show detail, but only where they look. Chemical sensors can measure specific things, not everything. A manipulator can collect samples, but not with the flexibility of a human hand. A sediment corer can preserve layers, but only from one location. A temperature probe can take measurements, but only where it is placed. Each instrument is a specialized sense. The vehicle is not all-seeing. It is a bundle of limited senses carried into darkness. This is why deep-sea exploration often produces narrow paths of knowledge. An ROV dive may create a line of video across a slope. An AUV mission may map a strip or grid. A sample may come from a single point. These are real observations, but they cover small portions of a large environment. The trench remains vast around them. It is easy to be amazed by what the machines show and still remember how much lies outside the camera beam. There is also the issue of disturbance. Exploration changes what it observes, at least a little. Lights enter darkness. Thrusters move water. Arms touch the bottom. Samples remove material. Vehicles make noise. In many cases, the disturbance is small compared with natural processes, but it still matters. Scientists want to observe deep habitats carefully, especially because some organisms may be slow-growing or poorly understood. Non-invasive methods are valuable, but they cannot answer every question. Sometimes a sample is needed. The challenge is to collect enough information while doing as little harm as possible. This is especially important in poorly known deep habitats. A vehicle may encounter animals that have rarely been seen. Some may be fragile. Some may live attached to rocks or buried in sediment. Some may react to light or movement. If the goal is to understand life in the trench, machines must be more than strong. They must be delicate. That is a difficult combination. It is hard to build something that can survive crushing pressure and also behave gently around a small animal living in mud. Data is another struggle, though it sounds less dramatic. Deep-sea missions can collect enormous amounts of information. Video, sonar, navigation logs, sensor readings, images, samples and notes all have to be stored, processed, interpreted and archived. A single dive may produce hours of footage. A mapping mission may produce huge data sets. The ship returns, but the work continues. Scientists must review footage, identify species, clean sonar data, correct navigation, compare samples, and connect observations to maps. The machine's struggle ends when it returns. The human struggle with the data may continue for years, ideally with coffee. So when people ask why our machines struggle in the midnight zone, the answer is not that the machines are poor. They are extraordinary. They are some of the most capable exploration tools humans have ever built. The problem is that the environment is stronger than ordinary assumptions. The deep ocean removes sunlight, blocks GPS, weakens communication, adds pressure, adds cold, adds corrosion, hides rough terrain, limits time, complicates recovery and makes repair nearly impossible. The machines are not failing because they are badly made. They are struggling because they are trying to work in a place that does not support easy work. And yet they do work. That is the impressive part. They descend through kilometers of water. They hold pressure out. They light the seafloor. They film animals that have never seen the sun. They map slopes that no human foot can touch. They collect mud that holds old events. They pick up rocks shaped by tectonic force. They place instruments that listen for future movement. They turn the trench from blank darkness into evidence. But they do this briefly, carefully, and with limits. A machine can visit the Puerto Rico Trench. It can reveal pieces of it. It can give us better maps, better images, better samples and better measurements. What it cannot do, at least not easily, is make the trench fully available to us. It cannot turn the deep sea into a place we can wander freely. It cannot remove the cost, the pressure, the distance or the difficulty of returning. It gives us access, but not ownership. It opens small windows, not doors. That distinction matters. Machines make exploration possible, but they also show us how far the trench remains from ordinary human experience. Every dive depends on technology acting as a substitute body. The vehicle sees for us, it touches for us, it measures for us. It carries our curiosity into a place where we cannot stand. And because every substitute body has limits, our understanding has limits too. This is not discouraging. It is simply honest. The machines have taken us farther than our bodies ever could. They have made the deep ocean visible in ways earlier generations could barely imagine. They have shown that the trench is not empty, not simple, and not beyond study. But they also remind us that there is a difference between sending a robot into the dark and truly being there. That difference becomes even clearer when we stop thinking about cameras and cables for a moment and think about the human body itself, soft, warm, air-breathing, full of delicate spaces, and completely unprepared for the weight of the deep. That difference becomes even clearer when we stop thinking about cameras and cables for a moment and think about the human body itself, soft, warm, air-breathing, full of delicate spaces, and completely unprepared for the weight of the deep. The human body is a remarkable thing, but it was not designed with the Puerto Rico Trench in mind. It is very good at many ordinary tasks. It can heal a cut, balance on one foot while putting on a sock, notice the smell of toast before the toaster admits anything has happened, and keep a heart beating without needing a meeting about it. It can walk, swim, sleep, digest, remember, and complain about a chair that is only slightly uncomfortable. But take that same body down into the deep ocean, and very quickly its talents become less useful. At the surface, we live inside a narrow comfort zone. We need air at a certain pressure, oxygen in the right amount, a body temperature kept within a small range, and enough water, food, and rest to keep the whole arrangement from becoming dramatic. The ocean, especially the deep ocean, offers none of this freely. It is cold, it is dark, it is heavy. It does not contain breathable air. It does not care about the lungs, ears, sinuses, blood, nerves, or bones of the visitor. To the trench, a human body is not a natural resident. It is a fragile, warm object from a very different world. Even before we talk about the deepest water, ordinary diving already shows the problem. Go a few meters underwater, and pressure begins to affect the air spaces in the body. Your ears may feel squeezed because the air behind the eardrum is being compressed. Divers learn to equalize pressure, allowing air to move into those spaces so the discomfort does not become injury. The mask, the sinuses, the lungs, and other air-filled spaces all become part of the pressure problem. The body is not a solid block. It is full of soft tissue, fluids, and small pockets, where gas behaves according to physical rules, not personal preference. At shallow depths, trained divers can manage these changes. They carry breathing gas. They control their descent and ascent. They monitor time and depth. They understand that coming up too quickly can be dangerous. They learn that the ocean is not a place for guessing. Even recreational diving done safely depends on respect for pressure. You cannot simply hold your breath and rise quickly from depth without risk. Expanding air in the lungs can cause serious injury. Dissolved gases can come out of solution and form bubbles in tissues and blood. This is the world of decompression sickness, often called the bends, and it is one of the reasons diving is careful, timed and planned. Now imagine trying to extend that idea not to 20 meters, or 30 meters, or even a few hundred meters, but to many thousands of meters. The Puerto Rico Trench reaches depths where the pressure is hundreds of times greater than at the surface. This is not a place a human body can adapt to by training harder, breathing calmly, or buying a better wetsuit. There are limits that courage cannot negotiate with. At trench depth, the problem is not that a person would feel uncomfortable. The problem is that the body cannot remain an ordinary body under those conditions. The pressure would crush air-filled spaces. Breathing gas at such pressure would become physiologically dangerous and physically difficult. The nervous system, lungs, circulation and tissues would face conditions far outside the range for which they evolved. This is why humans do not dive freely into the deep ocean. We enter only inside pressure vessels, or we send machines. The body must be protected from the deep, not exposed to it. A human-occupied submersible is, in one sense, a tiny piece of the surface world carried downward. Inside it, the pressure remains survivable. There is breathable air. There is some control over temperature. There are instruments, seats, controls and walls strong enough to hold the ocean out. Outside is the trench. Inside is a small bubble of human conditions. That bubble is everything. Without it, there is no human exploration at those depths. This can be difficult to picture because water feels familiar. We bathe in it, drink it, swim in it, wash dishes with it, and sometimes stare at it in a kettle, as if that will make it boil faster. But familiar water becomes something very different when stacked kilometers high. It becomes a force so great that the human body can only visit if wrapped in the engineering. The lungs are one of the first limits to consider. We breathe because air moves in and out of the lungs, allowing oxygen to enter the blood and carbon dioxide to leave. On land, this happens under conditions our bodies handle automatically. Under pressure, breathing gas becomes denser. The deeper the dive, the harder it can become to move gas in and out of the lungs. At extreme pressure, breathing ordinary air is not simply unpleasant. It becomes dangerous. The partial pressures of gases increase with depth, meaning oxygen, nitrogen, and other gases affect the body differently. Oxygen is necessary, but too much oxygen under pressure can become toxic. Nitrogen, which makes up most of the air we breathe at the surface, can cause nitrogen narcosis at depth, affecting judgment, coordination, and perception. Divers sometimes describe narcosis as a kind of drunkenness or mental fog. That may sound almost comical until you remember that poor judgment underwater is not a charming personality trait, it is a serious hazard. Deep divers use special gas mixtures to manage these problems, often replacing some nitrogen with helium, but even technical diving has practical limits. The deeper the dive, the more complex the gas planning, decompression schedule, equipment, training and risk. At the depth of the Puerto Rico Trench, these diving solutions are not enough. The pressures are far beyond anything ordinary diving can support. A person cannot simply breathe a clever gas mixture and stroll around the bottom. The body would still be exposed to pressure levels it cannot tolerate. This is where the trench stops being a diving destination and becomes a submersible destination, or more often, a robotic one. The blood and tissues also face the problem of dissolved gases. Under pressure, gases dissolve into body tissues more readily. During ascent, if pressure is reduced too quickly, those gases can come out of solution as bubbles. These bubbles can cause pain, nerve damage, breathing problems, paralysis, or death. Safe diving therefore requires controlled ascent and decompression stops, giving the body time to release gases gradually. This is already a concern for divers working at much shallower depths. The deeper and longer the exposure, the more serious and complicated the decompression becomes. That is one reason saturation diving exists for certain kinds of deep underwater work. In saturation diving, divers live under pressure for days or weeks in special chambers and work from diving bells, allowing their tissues to become saturated with inert gas. After that point, more time at depth does not greatly increase decompression time, but returning to normal pressure can still take days. This is highly specialized work, used at depths far shallower than ocean trenches. It shows human ingenuity, but it also shows the size of the problem. Even to work at a few hundred meters, humans require chambers, gas mixtures, support vessels, teams, procedures, and long decompression. The Puerto Rico Trench is not a few hundred meters down. It is many thousands. Cold is another limit. Deep ocean water is usually very cold. Human bodies lose heat in water much faster than in air. Even water that does not feel freezing at first can draw heat away quickly. Divers use wetsuits, dry suits, heated suits, and other protections depending on depth and conditions. But again, these are solutions for shallower water and controlled work. At trench depth, a person is not dealing only with cold water. They are dealing with cold combined with pressure, darkness, distance, and total dependence on life support. If the protective system fails, the body has no backup plan. The nervous system also belongs to the surface world. It depends on stable oxygen supply, proper gas exchange, temperature, blood flow, and chemical balance. Under extreme conditions, any of these can be disrupted. High pressure itself can affect biological systems. Deep diving research has shown that pressure and gas mixtures can influence the nervous system in complex ways, including conditions such as high-pressure nervous syndrome in very deep dives, tremors, dizziness, nausea, fatigue, and changes in mental function can occur under certain deep-pressure conditions. The details are specialized, but the simple point is clear. The human nervous system is not a casual visitor to high pressure. Then there is darkness. Darkness does not crush the body, but it changes the human experience of the environment. We are visual creatures. We orient ourselves by sight. In the trench, natural sunlight is gone. A person inside a submersible sees only what the lights reveal. Outside that beam is black water. The body may be safe inside the vehicle, but the mind still has to accept that outside the window lies a place where there is no open air, no horizon, no easy exit, and no familiar direction except the instruments telling you which way is up. This psychological side is not the main physical barrier, but it matters. Human exploration has always involved fear, judgment, and perception. A deep submersible dive places people in a small enclosed space, far below the surface, dependent on systems that must continue working. There is no stepping outside for a breath. There is no quick rescue by swimming upward. Even if the vehicle is functioning properly, the knowledge of the water above can be heavy in its own way. The trench is not only deep in distance, it is deep in consequence. Communication adds to that feeling. A person in a spacecraft can communicate by radio through empty space. A person underwater cannot rely on ordinary radio signals in the same way because seawater blocks them. Submersibles use acoustic communication or tethered systems depending on design. Acoustic signals can be limited, slow, and affected by conditions. The surface ship may be kilometers above. Help, if needed, is not immediate. Human presence at great depth is therefore not just a scientific choice, it is a serious safety commitment. This is why human-occupied vehicles are built with extreme care. Their pressure hulls are tested, their life support systems are checked, their emergency systems are planned, their dives are conducted by trained crews with support ships and strict procedures. A successful deep dive may look calm from the outside, but that calm is produced by engineering, training, and caution. It is not the calm of an easy environment. It is the calm of people respecting a place that can punish mistakes quickly. Even inside a strong submersible, human exploration remains limited. The vehicle is small, space is tight, dive time is finite. The crew can only see through windows or camera feeds. They can only travel so far along the bottom. They can collect only so many samples. They must return before life support, power, schedule, or safety limits are reached. A human dive can be incredibly valuable, but it is still a short visit into an enormous place. That shortness matters. To truly explore the Puerto Rico Trench, humans would need more than occasional dives. They would need repeated access across many locations and conditions. They would need to observe changes through time. They would need to map, sample, monitor, and return. Human-occupied vehicles are too costly and limited to do all of that alone. They are part of the toolkit, not the whole answer. Robots, autonomous systems, moored sensors, and ship-based surveys carry much of the burden because they can work in ways that human bodies cannot. The human body also creates ethical and practical limits. Every time people are sent into extreme environments, the value of the mission must be weighed against the risk. Scientists may want direct observation, but if a robot can collect the needed data with less danger, that may be the better choice. Human presence is powerful, but it is not always necessary. The trench does not become more scientifically meaningful simply because a person is physically inside a vehicle near it. Sometimes the best explorer is a sensor that does not need to breathe. Still, there is something about human presence that continues to matter. When people descend in a submersible and look out at the deep sea floor, they can interpret scenes in real time, notice unexpected relationships, and describe the feeling of scale in a way that machines cannot. A camera records, a person experiences. That does not make the data better by itself, but it adds a kind of attention that can be useful. The challenge is that the body must be protected so completely that the person is never truly in the trench in the way a fish or a microbe is in the trench. The human is in a capsule. The capsule is in the trench. That is as close as our biology allows. This is a humbling distinction. We can visit the deep, but only by refusing to let the deep touch us directly. We can look at it, measure it, and sample it, but the moment the pressure enters our world, the visit becomes dangerous. The submersible is not just a vehicle, it is a boundary. On one side of the boundary are lungs, skin, blood, warmth, speech, and the need for a safe return. On the other side are cold water, pressure, darkness, and a seafloor that has never needed permission from human bodies. The animals that live down there show a different solution. They do not resist pressure with thick metal walls. They are built for it from the inside. Many deep-sea organisms lack large gas-filled spaces. Their proteins and membranes function under pressure. Their bodies exist in balance with the environment around them. They are not being crushed because they are not carrying a surface world inside them. We are. Every human descent depends on carrying the surface downward in a sealed container. That makes the Puerto Rico Trench not just a place beyond easy reach, but a place beyond ordinary human belonging. We can study it, but we're not shaped for it. Our bones, lungs, eyes, and nerves come from land and shallow air. Our ancestors evolved under sunlight, gravity, weather, and breathable atmosphere. They did not evolve under 8 kilometers of Atlantic water. No amount of curiosity changes that. Curiosity builds tools. It does not rewrite the body. This is also why the phrase "explore the trench" needs care. On land, exploration can mean walking through a forest, touching the bark, hearing birds, smelling wet soil, and feeling the ground underfoot. In the Puerto Rico Trench, exploration is mediated. It comes through screens, windows, samples, sonar, sensors, and instruments. The human senses are extended by machines because the human body cannot go there naked and survive. Even when a person sits inside a submersible, the experience is filtered by glass, metal, lighting, cameras, and life support systems. There is no shame in that. Much of science depends on instruments extending senses beyond their natural limits. Telescopes let us see distant galaxies. Microscopes let us see cells. Seismometers let us detect earthquakes too small or distant to feel. Deep-sea vehicles let us enter a world our bodies cannot handle. Instruments are not a weakness. They are how human curiosity reaches beyond human anatomy. But the trench reminds us that instruments are necessary because the body has borders. We are not infinitely adaptable. We are land mammals with clever hands and fragile lungs. We can build machines that go deeper than we can. We can design pressure hulls, robotic arms, sonar systems, and autonomous vehicles. We can create maps from echoes and images from darkness. But we cannot turn ourselves into trench animals by wishing. The deep ocean does not bend around our biology. Our biology must stay protected from it. This protection is expensive, complicated, and limited. A human-occupied vehicle capable of deep work requires enormous support. It needs a ship. It needs a trained team. It needs maintenance, it needs launch and recovery systems, it needs careful weather planning, it needs testing and certification, it needs spare parts, procedures and emergency planning. The person inside may be the most visible explorer, but the dive is actually a group effort involving engineers, pilots, technicians, scientists, ship crew and planners. No one visits the deep alone, even if only a few people fit inside the vehicle. If something goes wrong, the depth makes rescue difficult. At shallow depths, divers may be assisted by other divers or surface teams. At great depth, options shrink. A disabled submersible or trapped vehicle becomes a serious emergency. That is why safety is built into every stage. Systems are redundant where possible. Emergency ascent methods are included. Dives are planned conservatively. The deep ocean is not a place for casual improvisation. It rewards caution more than bravery, and yet the human desire to see remains strong. There is a reason people still care about crewed dives even when robots can do so much. A human witness turns a remote place into a story. Someone can return and say, "I saw the wall of the trench. I saw the sediment drift in the lights. I saw an animal move across the bottom. I watched the darkness press against the window." That witness does not replace data, but it makes the place feel real to the rest of us. The Puerto Rico Trench needs both kinds of knowing. It needs the precise measurements that machines provide, and it benefits from the human ability to connect details into meaning. But when the question is why we cannot truly explore it, the body gives one of the clearest answers. We cannot move through it freely. We cannot remain there. We cannot build an ordinary station at the bottom with people walking in and out as if it were an Antarctic base. We cannot breathe the environment, tolerate the pressure, or repair ourselves if the boundary fails. Our presence must be brief, sealed, and supported from far above. So the trench remains physically close to Puerto Rico and biologically far from us. It is part of our planet, but not part of our natural range. We belong to the thin, habitable skin of Earth, the surface layer where air pressure, oxygen, warmth and sunlight allow bodies like ours to function. The trench lies below that skin, in a zone where life exists, but not life like ours. To reach it, we borrow the bodies of machines. And once those machines carry our eyes and instruments into the darkness, they begin to reveal something that may be even stranger than the difficulty of getting there. The Puerto Rico Trench is not empty. It is not just a crack, not just a hazard, and not just a depth measurement on a chart. It may hold forms of life, geological records, chemical processes, and traces of Earth's history that we have only begun to understand. And once those machines carry our eyes and instruments into the darkness, they begin to reveal something that may be even stranger than the difficulty of getting there. The Puerto Rico Trench is not empty. It is not just a crack, not just a hazard, and not just a depth measurement on a chart. It may hold forms of life, geological records, chemical processes, and traces of Earth's history that we have only begun to understand. That word, hiding, can be a dangerous one if we let it run off on its own. It can make the trench sound like a locked room full of sea monsters waiting politely for a documentary crew, and while the deep ocean has produced animals strange enough to make any imagination feel a bit underdressed, the real hidden things are usually quieter. They are not necessarily giant. They are not necessarily dramatic. They may be small, slow, pale, soft-bodied, buried in sediment, attached to rock, written in layers of mud, or present only as chemical traces that a human eye would miss completely. The trench may be hiding life, but not in the way a forest hides deer between trees. It may be hiding life because we have not looked in enough places, for enough time, with enough tools, at enough scales. A camera beam can show a fish, a brittle star, a coral, a sponge, or a shrimp-like animal crossing the mud. But it cannot show every microbe in the sediment. It cannot show every tiny animal living between grains. It cannot show every species that passed through before the camera arrived or emerged after the vehicle left. The deep ocean is not only difficult because it is dark, it is difficult because life there can be scattered, slow, fragile, and easy to miss. When people imagine life in the deep sea, they often picture bizarre fish with large teeth, glowing lures, and faces that suggest they have just received bad news from a dentist. Those animals are real in some parts of the deep ocean, and they are wonderful in their own unsettling way. But trenches are not crowded aquariums full of dramatic creatures posing under perfect lighting. Much of the deep sea floor can look quiet. A muddy plain may stretch beyond the lights. A small animal may move slowly. A track may show where something passed earlier. A burrow may suggest a resident that has no interest in being filmed. The lack of obvious activity does not mean the place is lifeless. It may simply mean that the life there operates at a pace and scale we are not used to seeing. In deep water, food is often limited. Sunlight does not reach the bottom, so there are no sunlit plants growing there in the ordinary way. Much of the energy that supports deep sea life comes from above, falling slowly as particles through the water column. Tiny fragments of dead plankton, waste, mucus, dust, and other organic matter drift downward in a steady fall, sometimes called marine snow. It is not snow you would want on a greeting card. It is more like the leftovers of the upper ocean, descending through darkness for days, weeks, or longer. To deep-sea animals, those leftovers can be dinner. This means many deep-sea communities depend on a slow supply line from the surface. A small change above can matter below. Productivity in the upper ocean, currents, storms, seasonal changes, and the movement of nutrients can all influence what eventually reaches the deep. The Puerto Rico Trench is therefore connected to the sunlit world, even though sunlight itself never touches its deepest parts. The trench receives material from life above, processes it below, and stores some of it in sediment. It is not cut off from the rest of Earth. It is connected by sinking particles, moving water, geological processes, and time. Microbes may be among the most important hidden residents. They do not need to look impressive to be powerful. Microbial communities and deep sediments can process organic matter, influence chemistry, and help shape how carbon and nutrients move through the ocean system. Some microbes live in the mud. Some may live around rocks or fluids moving through the seafloor. Some may survive under conditions that would seem unwelcoming to surface life. To understand the trench properly, scientists can not only count visible animals, they also have to study organisms too small to see without laboratory tools. That is one of the challenges of exploring what the trench hides. A camera can give a beautiful image, but biology is not only what appears on camera. A sample of sediment may contain microbial DNA, tiny animals, chemical signatures, and clues about food supply. A rock sample may hold attached life or mineral evidence of chemical processes. Water samples may reveal dissolved gases, nutrients, particles, and traces of organisms. Each type of sample opens a different window. But every sample comes from one place at one time. The trench is much larger than any sample box. There may also be deep-sea corals and sponges in parts of the region, especially on hard surfaces along slopes, seamounts, or ridges. These animals are not like the bright shallow water reefs many people picture, full of sunlight and tropical colour. Deep-sea corals do not need sunlight. They can live in cold, dark water, filtering food from currents. Some grow very slowly. Some provide structure for other animals, creating habitats in places that might otherwise be mostly rock or sediment. They can be delicate, long-lived, and vulnerable to disturbance. Finding them matters because they can show where deep habitats are richer and more complex than a plain depth map might suggest. A map can show a steep slope, but not whether coral lives there. A sonar image can show rough ground, but not whether sponges, fish, crabs, or brittle stars are using it. A camera can reveal these things, but only where the camera travels. This means the trench and its surrounding deep waters may contain small biological neighbourhoods that remain unknown simply because no vehicle has passed close enough with the right lighting at the right time. In the deep ocean, discovery can depend on a path only a few meters wide. This is why exploration cannot be reduced to visiting the deepest point. The deepest point may be famous, but life does not care about fame. Animals may gather where there is food, current, hard substrate, shelter, chemical energy, or favourable sediment, not necessarily where a map label says the maximum depth occurs. The most interesting biological communities may live on slopes, ridges, walls, or nearby seamounts rather than at the deepest axis itself. If we only chase the number, we may miss the living systems around it. The trench may also be hiding records of past earthquakes, landslides, storms, and environmental change. Sediment is one of the ocean's great record keepers. Layer after layer settles onto the seafloor. Some layers form slowly from ordinary background deposition. Others may arrive suddenly, when a slope fails or a sediment flow rushes downslope. A core taken from the bottom can show these layers stacked through time. To an untrained eye, it may look like tubes of mud, which is not the sort of thing that makes everyone leap from their chair, but to scientists that mud can contain a timeline. In those layers may be evidence of past events that no one witnessed. An old earthquake may have triggered slope failures. A turbidity current may have carried sediment into the trench. A tsunami-related event may have left records on land, while the seafloor holds another part of the story offshore. A change in grain size, chemistry, fossils, or organic content may reveal shifts in conditions. The trench floor can act as a collector, receiving material from the slopes above and storing it in deeper basins. This makes it valuable for understanding hazards, but also difficult to interpret. The problem is that layers can be complicated. Not every unusual layer means an earthquake. Not every deposit means a landslide. Storms, currents, biological activity, volcanic ash from distant sources, or gradual changes in sediment supply can all leave signals. Scientists have to compare cores from different locations, date the material, study its composition, and connect it with other evidence. The trench may be hiding history, but history in mud is not written in plain sentences. It's written in grains, chemistry, fossils, and disrupted layers. Reading it takes time. There may also be hidden clues in the shape of the seafloor itself. Some features may mark past landslides. Others may show fault movement. Some scarps may reveal where the crust has broken. Some basins may show where sediment has collected after repeated events. The map gives hints, but close inspection and sampling are needed to know more. A curved scar on a slope may be the edge of an old collapse. A rough debris field may show where material came to rest. A smooth surface may hide buried features underneath. The trench may be hiding events not because they are invisible, but because their evidence is incomplete. Chemistry is another quiet layer of mystery. The deep sea floor is not just rock and mud sitting underwater. Fluids can move through sediments and cracks. Chemical reactions can happen slowly under pressure and cold. Organic matter breaks down. Microbes use available energy. In some deep-sea environments, chemical energy can support life in ways that do not depend directly on sunlight. Hydrothermal vents are the famous example, though not every trench has the same kind of vent systems. The larger point is that chemistry can create habitats and processes that are not obvious from a simple image. If fluids seep from the seafloor in some areas, they may alter sediment, feed microbial communities, or attract animals adapted to those conditions. Cold seeps in other ocean regions can support communities around methane or other chemicals. Whether a specific place has such features requires direct evidence. You need sensors, samples, and repeated observations. A camera may show unusual life or mineral staining, but chemistry confirms the story. The trench may be hiding small chemical systems that are easy to pass over if the vehicle's path misses them. Even water itself can hide information. The deep water in and around trenches may have distinct temperature, salinity, oxygen, and chemical characteristics. Water masses move, mix, and carry signals from other parts of the ocean. Measuring those properties helps scientists understand circulation and how the trench interacts with the wider Atlantic. The deepest parts of trenches can sometimes trap or channel water in ways that affect oxygen, nutrients, and particles. That means the trench is not only a shape in the seafloor, it is also part of a moving water system. Then there are pollutants. This is a less comfortable thought, but it matters. Deep trenches, despite seeming remote, can receive human-made material. Plastic particles, chemical contaminants, lost gear, and other traces of surface activity have been found in deep ocean environments around the world. The deep sea is not protected by being far below us. Gravity is very patient. Material sinks. Currents move it. Food webs can carry it. Sediments can store it. The Puerto Rico Trench may hold evidence not only of natural history, but of human activity drifting downward from the surface world. This is one of the more sobering reasons to explore deep trenches. We may discover not just strange life and geological history, but also our own fingerprints. A place can be nearly impossible for us to visit and still be touched by us. That is a very human kind of contradiction. We cannot easily stand at the bottom, yet particles from our lives may arrive there. A plastic fragment does not need a research ship. It only needs time and the ocean's transport systems, which is both impressive and rather rude. The trench may also hide living species that science has not named. This does not mean there are unknown giant creatures waiting in the dark, though the internet would certainly enjoy that. More often, new species in the deep ocean are small, delicate, or similar looking to known animals until experts study them closely. A sponge may be new. A coral may be new. A worm, crustacean, mollusk, microbe, or fish may turn out to be undescribed. The deep sea is full of taxonomic patience. It does not announce a new species with a trumpet. It waits in a sample jar until someone with the right expertise, microscope, and persistence notices. This creates a bottleneck. Exploration may collect more biological material than experts can quickly identify. Deep-sea taxonomy is specialized work. Many groups of organisms require careful study. DNA analysis helps, but it does not replace expert comparison and description. So the trench may be hiding species not only because we have not collected them, but because some collected material still needs detailed study. Discovery is not always the moment the robot sees the animal. Sometimes discovery happens years later in a lab, when someone realizes that the specimen does not match what is known. There is also behavior to consider. Seeing an animal once tells us that it exists there. It does not tell us how it lives. What does it eat? How often does it reproduce? How far does it move? How does it respond to currents, food falls, earthquakes, sediment flows, or changes in oxygen? Is it rare or merely rarely seen? Does it live only in one habitat or across a range of depths? These questions require repeated observation. A single image can create wonder, but ecology needs patterns. Deep-sea animals may also move slowly or appear only under certain conditions. Some may be attracted to baited cameras. Some may avoid lights or vehicle noise. Some may burrow during the day, if day means anything down there, or follow chemical and food cues we do not yet understand. The trench may be hiding behaviour because our visits are too brief. We arrive with lights, stay for hours, and leave. The animals live there continuously. We are the strange interruption. Food falls are another hidden part of deep-sea life. When a large animal dies near the surface and sinks, its body can become a feast on the seafloor. Whale falls are the most famous example. They can support rich communities for years as scavengers, microbes, worms, and other organisms use the sudden supply of energy. In a deep trench system, occasional large food falls may be important but rare. If no camera happens to arrive near one, scientists may not see that part of the ecosystem. The trench may hide temporary abundance inside long periods of quiet. There may also be sounds and movements we rarely detect. The deep ocean is not silent. Earthquakes rumble, landslides may move sediment, animals produce sounds, ships pass above, water moves. Instruments can record some of this, but only if they are present, working, and close enough. A seafloor hydrophone or ocean bottom seismometer can turn hidden activity into data. Without instruments, many events pass unobserved. The trench may be hiding not because it is still, but because we are not always listening. This is especially true for small earthquakes and subtle seafloor movements. Land-based networks can detect many events, but offshore instruments improve resolution. If scientists want to know exactly where small quakes occur beneath the ocean, or how faults behave over time, they need more seafloor measurements. The trench may hide patterns of stress and movement that are too fine for distant instruments alone to resolve. Those patterns may matter for understanding hazards. Again, the secret is not dramatic. It is technical, precise, and important. The trench may also hide the limits of our own assumptions. That may sound philosophical, but it is very practical. Scientists often choose where to look based on existing maps, models, and expectations. That is sensible. You cannot sample everywhere, so you make informed choices. But informed choices can still miss surprises. If you expect life on hard slopes, you may spend less time over soft mud. If you expect a feature to be old, you may not sample it for recent change. If a map is too coarse, you may miss a small habitat. Exploration has to balance planning with openness to the unexpected. One of the most valuable things deep-sea exploration does is correct what we thought we knew. A map may suggest one thing. The camera shows another. A slope may appear barren. Close view reveals animals. A sediment core may show an event layer where none was expected. A sample may contain a species no one recognized. A sensor may record changes that models did not predict. The trench hides surprises partly because our first picture of it is always incomplete. It is tempting to ask what the most important hidden thing is. Is it life? Earthquake clues? Landslide records? New species? Chemical systems? Pollution? The honest answer is that we do not know, and that is exactly why exploration matters. The most important thing in the Puerto Rico Trench may not be the most dramatic thing. It may be a sediment layer that improves tsunami hazard models. It may be a microbial process involved in carbon cycling. It may be a fault structure that changes how scientists understand the plate boundary. It may be a biological community that shows how life survives under pressure. It may be a mapping detail that helps explain a past event. This is one of the quiet lessons of science. The valuable discovery is not always the one that looks best in a thumbnail. Sometimes it is a measurement, a correction, a sample, a pattern, or a small feature that helps many other pieces make sense. The trench may be hiding information that is useful not because it shocks us, but because it connects things. For Puerto Rico and nearby islands, the hidden hazard record may be especially important. If sediments preserve traces of past slope failures or earthquake-triggered flows, they can help scientists estimate how often certain kinds of events have occurred. If maps reveal unstable slopes, they can improve planning. If seafloor instruments record offshore earthquakes more clearly, they can improve models of fault behaviour. This kind of knowledge is not as visually dramatic as a strange fish in the headlights, but it may matter more to people living above the trench's influence. The trench may also hide evidence of resilience. Life in the deep ocean has endured darkness, pressure, cold, limited food, and geological disturbance for a very long time. Deep organisms have adapted to conditions that seem extreme to us, but normal to them. Studying them can reveal how proteins, membranes, metabolism, and ecosystems function under pressure. That knowledge may help biology more broadly. It may show us the flexibility of life, the limits of life, and the ways living systems persist where sunlight never arrives. Yet we have to be careful not to turn the trench into a fantasy of endless secrets. It is not magic. It is a real environment with real processes. What it hides because of distance, pressure, darkness, scale, and limited observation. The unknown is not an excuse to imagine anything at all. It is a reason to measure better. The best respect we can give a mystery is not to exaggerate it, but to study it carefully. That careful study takes time. A trench ecosystem cannot be understood by one dive. A geological record cannot be read from one core. A hazard system cannot be modelled from one map. A species cannot be understood from one photograph. Each glimpse matters, but each glimpse sits inside a much larger uncertainty. The Puerto Rico Trench may be hiding many things, but it is also teaching us how slow real knowledge can be when the place being studied is difficult to reach. There is a strange comfort in that slowness. Not every part of Earth has been turned into a quick answer. Not every deep place has been flattened into certainty. The trench remains a reminder that the planet still contains areas where patience is not optional. It asks for better maps, better vehicles, better sensors, better sampling, and better long-term observation. It asks for scientists who are willing to accept partial answers and keep working. If we could drain the Atlantic for one impossible afternoon, the Puerto Rico Trench would no longer be a dark, hidden place. We would see its walls, slopes, scarps, basins, ridges, debris fields, and sedimented floor. We might see where landslides tore away pieces of the margin. We might see channels where sediment moved. We might see rocky habitats, soft plains, and strange textures in the mud. But even then, even with the water removed, we would not understand everything. We would still need to ask when features formed, what lives there, how the crust moves, what the sediments record, and how the system changes through time. That is the deeper point. The trench is not only hidden by water, it is hidden by complexity. The ocean makes it hard to reach, but the science makes it hard to finish. A place can be visible and still not be fully understood. The Puerto Rico Trench is both concealed and complicated, and that is why it continues to matter. For now, our machines bring back pieces, a view of a slope, a map of a basin, a sample of mud, a record of shaking, a glimpse of coral, a trace of chemistry, a strange animal crossing the lights and disappearing again. These pieces do not solve the trench. They make it more real. They turn it from a dark shape on a chart into a working landscape with life, history, hazards, and unanswered questions. And as we gather those pieces, we arrive at a gentle but honest conclusion. The reason we cannot truly explore the Puerto Rico Trench is not one single barrier. It is the combination of all of them. The depth, the pressure, the darkness, the active seafloor, the limits of maps, the struggle of machines, the fragility of the human body, and the sheer amount we still do not know all overlap. The trench is not refusing us out of drama. It is simply larger, deeper, and more difficult than our ordinary ways of knowing. And that leaves us floating above it, listening carefully, still learning how to look. Floating above it, listening carefully, still learning how to look, we begin to understand why the Puerto Rico Trench keeps its distance from us. Not because it is mythical, not because it is unreachable in every sense, not because science has turned away from it. It remains difficult because every part of it asks for more than ordinary exploration can give. It asks us to map through water that blocks our view. It asks us to send sound downward and wait for echoes to climb back. It asks our machines to survive pressure that would crush most things we build without a second thought. It asks our instruments to work in darkness, cold, salt, current, and silence. It asks our scientists to read mud as a record, slopes as warnings, faults as hidden lines of stored energy, and tiny living creatures as evidence that life does not need comfort in order to continue. And perhaps that is the important thing to carry with us as we reach the quiet end of this journey. The Puerto Rico Trench is not unexplored because it is ignored. It is not unknown because humans have lacked curiosity. If there is one thing our species has never lacked, it is the urge to poke a careful instrument into a dark place and ask, "What's this then?" We have crossed oceans, climbed mountains, entered caves, drilled ice, landed probes on other worlds, and sent machines into parts of Earth where our own bodies would last about as long as a biscuit in tea. The trench remains only partly known because it is hard in several ways at once. A place can be deep and still simple. A place can be dark and still stable. A place can be remote and still easy to map. The Puerto Rico Trench is deep, dark, active, wide, steep, pressurized, biologically subtle, geologically complicated, and close enough to human communities that understanding it matters beyond curiosity. It is not just a scientific puzzle, it is a neighbour beneath the sea. That may be one of the strangest parts of the whole story. This hidden landscape sits near Puerto Rico, near the Virgin Islands, near coastlines where people live beneath warm air and familiar skies. Above the trench are waves, boats, passing weather, and the ordinary blue of the Atlantic. Nearby are streets, beaches, harbours, music, kitchens, school mornings, evening lights, and all the daily human things that make a place feel real. Below that same ocean, the seafloor drops into a cold darkness where the water presses with a force that turns exploration into engineering. It is easy to imagine mystery as something far away, a distant planet, a moon of Jupiter, a crater on Mars, a signal from another star. But the Puerto Rico Trench reminds us that mystery can sit beside us on the map. It can lie under shipping routes, near islands, beneath waters that people have looked at for centuries. We do not have to leave Earth to find places beyond easy reach. Earth still has rooms we cannot simply walk into. That thought can feel unsettling at first. We live in an age of maps, satellites, search bars, weather models, and phones that can tell us the nearest place to buy a sandwich in a city we have never visited. The world often feels completely available. Tap, zoom, scroll, search, and there it is. But the ocean resists that habit. It does not let us see through it with ordinary light. It does not hand over its floor just because we have drawn blue across a map. It makes us work for every detail. The surface of the sea can trick us into thinking we know what lies beneath. It covers everything with one moving sheet. It hides mountains and canyons under the same colour. It gives a trench and a shallow shelf the same waves. Stand on a shore at night, and the ocean may look like a single dark plain stretching away from you. But under that plain is structure. There are slopes, steps, cracks, soft plains, rocky ledges, sediment layers, animal trails, old scars, and hidden records of movement. The Puerto Rico Trench is one of the places where that hidden structure becomes extreme. The Atlantic floor does not merely dip there. It falls into a deep and complicated boundary region shaped by the movement of plates. The seafloor has been bent, broken, shifted, and covered again by sediment. It holds clues to earthquakes and underwater slope failures. It may hold records that could help us understand past tsunamis. It may hold biological communities that have adapted to darkness and pressure in ways we have barely begun to study. And still, we cannot simply go down and know it. We can send an ROV with lights and cameras, but it sees only where it looks. We can send an AUV to map closer to the bottom, but it must return before its power runs low. We can lower instruments, but they may sit alone for months, hoping their seals hold and their batteries last. We can collect sediment, but each core is only one narrow thread from a large and uneven fabric of mud, rock, and time. We can take samples of water and life, but each sample is only a moment removed from a place that continues after the ship leaves. That is why true exploration of the trench is not a single act. It is not one dive, one map, one dramatic descent, or one photograph with a proud caption. True exploration would mean repeated observation across years, detailed maps across wide areas, samples from many settings, Long-term instruments listening from the bottom, better understanding of faults and slopes, careful study of deep life, and enough patience to admit when the trench has not yet given a clear answer. The word truly matters. We can explore the trench in pieces. We have explored pieces. We will explore more. But truly knowing it would require a level of access that the deep ocean does not easily allow. A forest can be revisited tomorrow. A mountain can be climbed again next week if the weather and knees agree. A coastline can be surveyed every season. But a deep trench requires ships, equipment, funding, weather windows, trained crews, and technology that must survive conditions very far from the human comfort zone. The trench makes curiosity expensive. It makes patience necessary. It makes every answer arrive with a small label that says, "More data needed," which is not always exciting, but is usually honest. There is a calm lesson in that honesty. Not every mystery needs to be solved quickly to be worth studying. Some places teach us slowly because that is the only way they can be known. The Puerto Rico Trench teaches through echoes, samples, pressure readings, maps, and brief flashes of camera light. It teaches through what fails as well as what succeeds. A broken instrument teaches engineers what to improve. A blurry map teaches scientists where to return. A missing sample teaches the team to redesign the tool. Even difficulty becomes part of the learning. And the difficulty does not make the trench empty. If anything, it makes each glimpse more valuable. A pale animal moving across the sediment. A coral attached to a hard surface in the deep. A slope scar revealed by sonar. A layer of disturbed mud inside a core. A small earthquake recorded by a seafloor instrument. A chemical reading that suggests something unusual below. These are not complete answers, but they are real pieces of a place that spends most of its existence beyond human sight. It is possible that the Puerto Rico Trench will never become familiar in the way land can become familiar. We may never know it as we know a valley we can walk through, a road we can follow, or a beach where the same rocks appear each low tide. We may never build a permanent human station at the bottom, or watch its slopes every day with our own eyes. The pressure, distance, and darkness may always keep it partly separate from us. But perhaps that is not a failure. Perhaps some places are not meant to become ordinary. That does not mean we should leave them unknown. It means we should approach them with care. The trench is not a blank space for fantasy, and it is not a trophy to be claimed. It is a working part of Earth. It is a deep geological system, a possible hazard source, a habitat, a sediment archive, and a reminder that our planet still contains places where knowledge must be earned slowly. When scientists study it, they're doing more than satisfying curiosity. They're improving maps that may help hazard planning. They're learning how the seafloor behaves near populated islands. They're documenting life in deep water. They're building better tools for future exploration. They're testing what technology can do in one of Earth's harshest environments. They're also reminding us that the ocean is not empty space between lands. It is the largest environment on the planet, and much of it still lies beyond casual understanding. That matters for all of us, even those who live far from Puerto Rico, far from the Atlantic, far from any coast at all. The deep ocean helps regulate Earth's systems. It stores carbon. It circulates water. It holds biological communities. It records past events. It receives material from the surface. It connects geology, chemistry, climate, and life. The Puerto Rico Trench is one part of that larger ocean, but it shows the larger truth clearly. The planet beneath us is more complicated than our daily lives make it seem. Most days, we do not need to think about trenches. We wake up, check the time, make tea or coffee, answer messages, misplace something important, find it in a place we definitely already checked, and move through the familiar routines of being human. The deep ocean continues beneath all of that without asking for attention. Plates move, sediment falls, small animals feed, water circulates, faults store stress. Instruments, if we've placed them there, listen in the dark. There is something grounding about that. The world is larger than the part we use each day. Beneath the surface, processes continue whether we notice them or not. The Puerto Rico Trench does not hurry. It does not need to be visible. It was shaped long before us, and it will remain long after any one expedition has finished its work. Our visits are brief. Its timescale is not. And yet, our brief visits matter. They matter because knowledge is built from small acts repeated carefully. One survey adds detail, one sample adds context, one instrument adds time, one dive adds images, one study adds interpretation. Over years, those pieces accumulate. The trench may never be easy to explore, but it can become better known, not fully captured, not fully solved, better known. That is often the most realistic and most useful goal in science. Not final certainty, but better understanding, a clearer map, a stronger hazard model, a more complete species list, a more accurate picture of the plate boundary, a better way to build machines that survive the deep, a better sense of what we still do not know. As we drift now above the Puerto Rico Trench in thought, the surface seems quiet again, the waves move. The night air softens. Somewhere beyond the water, Puerto Rico rests under its own lights, and the trench remains below, out of sight, holding its pressure, its darkness, its slopes, and its long record of change. We cannot see it from here, but we know enough now to feel its presence differently. Not as a monster beneath the water, not as an empty hole, not as a simple line on a map, but as a deep part of Earth that asks for respect. So, if you are listening from somewhere near the sea tonight, perhaps the next time you look out at dark water, it may feel a little less flat. Beneath the surface there may be shelves, slopes, valleys, ridges, and deep places hidden under the same quiet waves. If you're far inland, perhaps the thought still travels to you. The ocean is not just at the shore. It is part of the whole planet's story, connected to weather, climate, life, hazards, and the slow movement of Earth itself. And if this quiet journey into the deep has brought you a little calm, or given your mind something wide and slow to rest upon, I would be ever so grateful if you liked the video, subscribed, and shared this space with someone else who enjoys learning without being rushed. There is always more to explore here, not always in the places we expect, and not always with answers that arrive quickly. Sometimes science is a lantern held over a very large darkness. It does not light everything at once. It lights enough for the next careful step. Tonight, that lantern has taken us over the Puerto Rico Trench, down through the weight of the Atlantic, past the limits of maps and machines, across restless slopes and hidden records, and back again to the surface where we can breathe easily. The trench remains below, still difficult, still partly unknown, still waiting in the deep water north of Puerto Rico. And maybe that is all right. We do not need to own every mystery in order to value it. We do not need to stand at the bottom to understand that it matters. We only need to keep learning carefully, honestly, and with enough humility to admit that Earth still has depths beyond our reach. So settle softly now. Let the imagined ship drift on the quiet surface. Let the instruments rest. Let the lights of the deep vehicle fade from view as it rises slowly through the dark water. Above it, the ocean becomes lighter, then blue, then bright again. Below it, the trench returns to its long silence. Sleep well, fellow traveller, wherever you are listening from tonight. The world is still wide, the sea is still deep, and beneath the calm surface there are places we're only beginning to know.